All right, everybody, welcome to the second day of the joint meeting. This is the ocean session. The polar session is in the Damon room. That's up and around and back that way, if that's what you're looking for. We'll start our morning session here. We have 5 talks this morning, starting with Mats Benson in Norway. We will go till 10:05. There's a break at 10:05 till 10:30. During the break, there's 3 posters out here, just out by the refreshments to take a look at. The restrooms are down by the security or up on the second floor and back by the library, I think. Any other announcements? The cafeteria is open today for lunch. They're not serving a hot lunch, but there's an array of cold lunch options, sandwiches, and they are taking payments from non-employees. So if you want to have lunch here, you're welcome. If you brought lunch or if you want to buy lunch, you can. If you would rather go down the hill to Table Mesa Shopping Center, I'm happy to drive people if you need a ride. Let's get together at lunch if anyone wants to do that. That's all my announcements. So our first talk is Mats Benson. Quickly though, before we do that, when we do Q&A, we'll use the room mics, not the one that I'm holding right now. So just make sure to speak loudly. If you're online and you have a question, just make sure to unmute yourself before you speak. We will be monitoring if you raise hands, so we'll try to call on you and just unmute yourself. All right, with all that out of the way, Mats, are you ready?
Yes.
All right, our first talk is from Mats Benson. Go ahead, Mats.
Good morning, everyone. We'll talk about our experience with the BLOM and the ALE method in Earth system modeling. So first, BLOM, that is the Bergen layered ocean model, and it is the ocean component of NOR-ESM. NOR-ESM is based on CSM, and further BLOM and MOM6 share the use of the ALE method and hybrid vertical coordinate. So therefore it feels natural and useful to follow and contribute to this meeting. So I will briefly introduce the vertical coordinate views. Then I will talk about a recent development of how we try to make the reference density adapt to the changing model state. If time permits, I will also talk about slowly developing issues in the layer structure that we've seen in multi-century simulations and how we have gone about to solve that. So first, about the BLOM vertical coordinate. So the arbitrary Lagrangian layering method that was recently implemented in BLOM, in addition to what we have used before, which is bulk mixed layer and an isopycnic formulation. So the ALE method is a kind of a 2-step approach. First, there is a truly Lagrangian phase, and then a remapping of variables to desired vertical grid in the second phase. In this regridding and the choice of vertical grid, there is much flexibility, and we try to exploit that as I will describe later. When we use the ALE method in BLOM, we support 2 vertical coordinates, constant pressure levels, and hybrid. For the hybrid coordinate, which are our kind of main approach, is hybrid between continuous isopycnous, so that is prescribed potential density, referenced at 2000 decibar at layer interfaces, and constant pressure levels towards the surface. Just to show these 3 approaches that we support, this is showing potential temperature in the Pacific section at the end of the second cycle of GRA forcing. To the left is the previous formulation we had, isopycnic with a bulk mix layer. In the middle, we have the hybrid coordinate, constant pressure levels at the surface, isopycnic in the interior. And to the right, constant pressure levels. And all configurations produce reasonable simulations, but our kind of main focus in this talk and our main choice for Earth system simulations is the hybrid coordinate. Then I will talk about how we go about to try to adapt the choice of reference densities to a changing model state. And the primary motivation to do this is to ensure a coherent approach to layer structure when we for a wide range of forcing scenarios. And the figures here show a bit of the issues that we have experienced in the past. This is from CMIP 6 simulations with NORIS M2. And what is shown is layer index in the Pacific section after 500 years into the pre-industrial control simulation, that is the upper panels, and then the lower panels is after 500 years with the abrupt 4 times CO2 increase. And the left panels are full depth, showing the section in full depth, and the right panels is assumed in the upper 500 meters. And what we can see is that particular here, upper ocean, when the model warms, we lose vertical resolution. There's a thick layer forming beneath the mixed layer. This is not present in the pre-industrial control. So this is not desirable. Physics will potentially change when exposed to a very different vertical resolution here. And also we ran into numerical instability. So we were not able to go much past beyond 500 years for 4 times CO2 experiment. A secondary motivation is to when the model drifts away from initial conditions, how can we ensure the optimal use of the vertical resolution? So this is how we try to go about this density adaptation. So we describe the reference potential density by a functional form that consists of a cubic Bezier curve. That's the blue curve shown here. And we also we connect that smoothly to two parabolas and the surface and the bottom to capture more extreme water masses. So typically, very dense water masses will be deep Mediterranean water masses. Very light water masses will be typically Baltic Sea water masses in the global ocean. But we need to be able to handle those. These are represented in a non-dimensional vertical coordinate set ranging from 0 to 1. We use the Bezier curve because it is smooth, well-behaved, and it's easy to control the slopes of endpoints. Then, of course, we want the functional form to be able to describe what we need, but also we want to make it as simple as possible in terms of what kind of parameters to control. What we prescribe is the range of these parabolic regions. We also prescribe the potential density slope or the sigma slope, this orange line, that kind of sets the density resolution in a deep ocean, which is the bulk of the water masses. And we also say that the Bezier curve is defined by these 4 points, P1, P2, P3, and P4. And the second, third, and fourth point is on this slope to constrain that. We also prescribe the height of this P3 Bezier point. But we do allow the sigma value of P4 and this bottom value here to change during the simulation. And the target there is to keep prescribed mass fraction contained in this parabolic region here. And finally, we allow this Bezier point P1 and P2 to change to adapt or to optimally occupy the mixed layer with constant pressure levels. And some details about the optimization. So we collect a model, a monthly model climatology of various parameters that goes into the optimization from the preceding year. We have a target mass fraction within the densest parabolic distribution that we have currently set to 1%. So 1% of the ocean mass will be in that parabola. Then we try to optimize this, the extent of the pressure levels so that they optimally occupy the mixed layer. And then we adjust these two parameters, P1 and P2. And there we try to minimize a cost function described here that we sum up for all the months, all the grid cells. We weight by the area, grid cell area. We use the squared logarithmic of this fraction here, where PML is the thickness, the model thickness of the mixed layer, and PML star is the thickness of the mixed layer that we will get if we optimally occupy the mixed layer with constant pressure levels. The optimization doesn't add much computation or computational cost. We only do this once a year. And to avoid having single anomalous years impact the parameters too much, we also have we apply a time filtering, so over the 10 years e-following time scale to adjust the model parameters. So we tested this in pre-industrial control simulation with and without density adaptation. And also we try to stress the method by using 4 times CO2 and 8 times CO2 forcing. We configure Blom with 72 vertical layers. The PI control is 80 years, and 4 times and 8 times CO2 simulations are 50 years, branched at year 30. So in these figures here, we see how these parameters we allow to evolve, how they change. We see an additional strong adjustment of parameters from the initial value in the PI control. PI control is in blue. In these figures, the circles are the annual optimization, and the line is the actual time-filtered adjustment of the parameters. Then we see when we add 4 times CO2, that's the red lines, 8 times CO2 is the magenta color. And we see that several of these parameters change quite a lot when we really force the model. In this lower left panel, we can see the kind of the reference densities at the end of the simulation, and we see that when we have these strong forcing experiments, the reference densities have been adjusted to tackle the much lighter water masses in the surface. So if you look at what is shown here is layer index in a Pacific section at the end of the pre-industrial control and the 4 times CO2 simulations. The upper panels are the pre-industrial control. Lower panels is the 4 times CO2. What is shown here is simulations with no adaptation to the far left, showing you the full depth of the Pacific section. Here is with adaptation. So we see in the pre-industrial control, the layer structure at depth doesn't change much, as we would hope as we would expect. If we have no adaptation in the 4x CO2, also the layer structure at depth is very similar to the pre-industrial control after 50 years. If you add adaptation, we see that the layers change quite a bit, which layers the water mass will occupy. So small changes in the reference densities will make quite an impact here. If you zoom into the upper ocean, with no adaptation, we see in a 4x CO2 simulation that we lose resolution in the tropical Pacific. While if we have the adaptation, we maintain resolution and we have a fairly similar layer structure towards the surface as in the PI control. If you go to 8x CO2, exactly the same. We see this region with loss of vertical resolution. With adaptation, this is resolution is maintained quite well. So then one can ask, does this change the simulation? Does it introduce a lot of mixing or other things? So what is compared here is to the left, pre-industrial control with and without density adaptation, and to the right is 4x CO2 with and without reference density, with and without density adaptation for the final 30 years of the simulation. So we see for quantities here, this is global mean temperature. So the heat uptake of the model, it's quite similar. The PI control is slightly imbalanced, so it heats a bit, but at a similar rate in both simulations. AMOC is behaving quite similar. This is the lower time series. That's the Drake Passage transport. It's declining in both. It's not so good, but it's consistent with and without adaptation. This is zone mean temperature, so very small differences in the zone mean temperature. And the same story really for the 4x CO2. So it seems to be not impacting overall aspects of the simulation. So finally, I just want to touch on something that we saw basically 6 months ago, so quite late in the development of the CMF7 version of NORI-SEM. So that was at the time when we had produced fairly long, or not very long, but at least multi-century pre-industrial simulations. And then we saw layer structure really collapsing at depth after going beyond a few hundred years of simulation. The upper panels are showing the global overturning circulation, and we also see very undesirable circulation from this collapse in the layer structure. In these simulations, we also had very strong oscillation in the Southern Ocean sea ice extent, showing some examples from various test simulations that we thought could or could not be related to this collapse of the layer structure. But in trying to find a solution for to kind of maintain good layer structure, we created daily or animations with daily layer structure, so very high frequency diagnostics to inspect what was happening. And during that phase, we saw also other things happening in the model, and we revealed that there were some spikes happening in the layer structure that was caused by the restratification parameterization. So when we had diagnosed deep mixed layer depths feeding into the parameterization that could cause very erratic behavior. So possibly that in combination with collapsing layer structure was the reason for this solar motion oscillation or variability in our model. So we solved this layer structure by constraining the local vertical thickness. We introduced a minimum thickness that is essentially that's specified as a fraction of the average thickness of the layer itself and its closest neighbors. So then we have an adjustable parameter here, gamma, so we can adjust that we can use to tune this. That was one thing. And for the restratification parameterization, then we constrained the mixed layer depth going into the parameterization. So we say that this is a kind of fraction of the boundary layer depth. So that is how we limit that. And basically, we constrain the MLD going in there by saying it cannot be deeper than 3 times the boundary layer depth. That is our constraint on that. So if you look at 200-year simulations, this is before we did anything, that's the far right. What we found was that it is very sensitive to this gamma parameter controlling this minimum thickness. If we use a gamma of 0.6, undesirable structure developed. With 0.8, we got very smooth and maybe too smooth structure. So we ended up, and what you're using now is a gamma of 0.7. So now you're able to run at least long simulations without this issue happening, and hopefully there will be no more surprises down the road. So that's it. Thank you.
Thanks, Matt. It's very interesting. I think we just have time for one question because I want to keep us on track this morning. So, Gustavo.
Thanks, Matt. I might have missed, how often do you do the adaptation? How often you change the target densities?
So we do the optimization once a year. And then that is fed into a time filter. So we actually adjust the parameters every time step, but with a very small adjustment every time step.
Thank you.
All right. Thank you, Matt. And keep us on track. I'm going to ask Rita to come up, but anyone else who has questions for Matt, I'd invite you to follow up with them online, send them an email or something. All right. I'm working.
Nice. Do I need to?
Yeah, we should.
Okay, can you hear me well? Yeah. Okay. I don't see it. That's what it's.
Go ahead. Thank you, Mark. Rita.
Yeah. Okay.
Thank you, Ian. Good morning, everyone. So today I'm going to speak about CFORCE, which is the next generation data set for forcing ocean sea ice coupled models. And this is the work that we are doing in the Ocean Group with a number of collaborators in other places as well. So this data set for forcing ocean sea ice models is the successor of Core 2 and GRA55DO forcing. However, this time we base it on ERA5 reanalysis. And the reason why we do it is because ERA5 is state-of-the-art trusted reanalysis product that has a high spatial and temporal resolution that is suitable for forcing high-resolution ocean and sea ice models. So AR5 has a quarter-degree spatial resolution and has hourly data. This reanalysis is up to date and is updated near real time. It's going back in time as far as possible. So it covers the period from 1940 until the present day with some insignificant lag. We have the buy-in, support, and collaboration with the ECMWF group that produces this reanalysis product. So we collaborate with them. They know about this effort and they do support this effort. And they do have the institutional commitment for continued production of this reanalysis data set. And also in the future, in a year or so, they will release the ERA 6 reanalysis and all the corrections and things that I'm doing now for ERA 5, like all this code and scripts that I'm developing, will be possible to use for ERA 6 reanalysis as well. And there is no redistribution issues, so it's easy to download and use this reanalysis. So basically, we in this project, we largely follow the process that has been described by Tsujino et al. 2018 paper when they were creating GRA55DO reanalysis that was based on GRA55 forcing. That is not continued anymore and not supported anymore. So we had to switch to more modern reanalysis product. And in this project, there are several big stages. The first stage was to do the adjustment of the main variables that are used for forcing ocean models. Then to create the data set with the river and the glacier runoff and discharge. And the third step is to do the global heat and freshwater balance adjustments with a strategy to capture the historical warming trend. Excuse me. Oh, sorry, I just thought someone. Okay, sorry. I thought that maybe someone can hear or something. Okay, so, and I have, at this point, I have done the adjustment of the main variables, and we created the data set with the river and glacier runoff and discharge, and we are working now on the global heat and freshwater adjustments. So this table summarizes all the adjustments that we've made to the main parameters that are used to force the ocean models. And here I present the variable, the reference data set that we used, the base period adjustment type, and what was new compared to GRA55DO reanalysis. So basically the idea here is that we used compared to GRA55DO, we basically used the newer versions of the data set where it is possible. And also, we used a slightly different approach for the river runoff and the Greenland and Antarctic runoff as well, but I'm going to speak about it in more detail later. So we'll start with the temperature. So there is a known issue in ERA 5 reanalysis, which is a warm bias in the Arctic Ocean. And we looked into it ourselves, and this bias can reach up to 10 degrees. So it's a big bias. And when groups are running ocean models forced by the raw ERA 5 reanalysis dataset, sometimes it leads to all the ice in the Arctic melting, which is not ideal. So here and indeed, when we compared ERA 5 with the multi-reanalysis mean, it did have warm biases in the polar latitudes and slightly colder biases elsewhere. So we corrected the temperature, ERA 5 temperatures, using the weighted mean of several reanalysis products. So this is the list of the reanalysis products that we've used. And we did so by introducing the monthly offset that was based on the 1980 to 2015 reference period, which basically means that, so we introduce like the same offset for all Januaries from the period from 1940 until present day. And when we looked at the time series of the global mean surface air temperature, in ERA 5, so the black line here shows the time series in the raw ERA 5 reanalysis, and you see that it's generally lower than all other reanalysis or GRA55DO. And the blue line here shows the corrected ERA 5 reanalysis. So it becomes, it's like more consistent with multi-reanalysis product, like with this reanalysis, and also goes closer to GRA55DO, even though it's not the same thing. So for correcting specific humidity, before we did the main correction, we did do some computation to preserve the relative humidity because we adjusted the temperature, so we needed to preserve the relative humidity. And we did so by recalculating the saturation specific humidity at this adjusted temperature, and then updated the specific humidity using the original relative humidity and its new saturation value. And after that, we also applied monthly climatological correction using the same multi-reanalysis ensemble. Here we used multiplication factor instead of offset. The same idea as temperature correction, but the multiplicative factor instead of offset. This is the pattern that, like, this is the correction basically that we applied to specific humidity that is averaged over all months. And the adjustment over most of the oceans are within 5% here. So these are the corrections that we applied to radiation, to the short and long wave radiation. And we had to basically reduce the shortwave radiation in these regions, which is it's a known issue in a lot of reanalysis that they don't get the cloud cover very well. So these biases in AERO5 that exist may be related to that. And you can see here that in long wave radiation, we have generally lower biases in reanalysis than in the shortwave. So for surface winds, we had to do it in 2 stages. On the first stage, we had to do the despiking of the surface winds. There is one of the known issues with AERO5 that sometimes in some locations, it has a very rare 10 meters winds spikes up to 300 meters per second. So that shouldn't happen. On this map, I'm showing the locations in the world where it happens. I apologize if you can't see it very well, but like there are no points that are in the open ocean, but some of the points are in the coastal areas, which can have an impact on the ocean variables as well. So these spikes, they seem to be linked to the 4D bar window edges, because these events, they don't last for 12 hours and they typically end when the new assimilation cycle begins. So it's some issue with assimilation. And basically what we've done here, we detected these events using 50 meters per second threshold. I tried to reduce this threshold, but then we start capturing the real storms. And in total, we have 82 events from 1979 to 2024. And again, the map shows the location of these events. Apart from the spikes, it's not just the spikes, it's also, I'm showing here the snapshot at the peak of one of the events. It's not just the spikes, it's this ripple-like structures. So if we can't just use some threshold and say that if it's above 50 meters per second, just keep it 50 meters per second. Because we also have, this structure, even though it doesn't reach the threshold, it's still unrealistic. It's not how it should look like. So basically what we've done here is that for these events, we did some time-space interpolation that was applied to the winds, and we did it for the area that is plus or minus 20 degrees from the epicenter of the event. Interestingly, I also checked whether these peaks, whether these spikes exist in sea level pressure, radiation, precipitation, temperature, and humidity, and there is no artifacts in sea level pressure or radiation or precipitation, but we do see these spikes sometimes in temperature and humidity. So we did the same despiking for them as well. On the second stage, we actually corrected the wind vectors. So here we use the CCMP dataset, which is it's a cross-calibrated multi-platform satellite product, which basically it's a cross-calibrated product that is blending all available scatterometer and radiometer data. And this is new compared to GRA55DO in the sense that GRA55DO just used ASCAT and SSMI, and here we basically use the product that blends them all together, cross-calibrates. So when we have the longer time coverage and hopefully more trust in this product. So we applied to the wind vector, we applied both scaling factor and also the rotation factor. And the rotation factor has been applied based on the same complex EOF method that was used in Tsujino paper for GRA55DO. But basically it gives very similar results to Lage and Jaeger 2009, with the exception that it treats more carefully the regions with low winds when we have the change in the wind direction. So when we have like 180-ish degrees change in the wind direction, it just treats it more carefully, but otherwise it's very similar to Lage and Jaeger approach. For precipitation. So for now, we did not do any precipitation correction in AERO5. And the reason for it is that generally, AERO5 precipitation is rather good. at least over ocean, compared to other observational-based data sets. They did a lot of improvements compared to previous generations of reanalysis. And here, as an example, I'm showing the time series of precipitation in so the GRA 55 reanalysis in blue, GRA DO, so this corrected data set that was a previous generation, that's just shown in red, and ERA5 precipitation is shown in green. So like even raw ERA5 precipitation over ocean is already very similar to GRA 55 DO. And like there are some issues with precipitations that are known and documented. For example, there are some rain bombs in ERA5 over the high mountainous regions in Africa, which will be relevant for land model, but for now we decided to keep it aside. And also we pointed to the fact that ERA5 has some biases in the snow in Arctic and Antarctic regions. TBD what we're going to do with it, but yeah, this is what's going on for now. So for the runoff, for the liquid and solid runoff, so ERA5 doesn't have any information about solid and liquid discharge, as well as the river runoff. So basically what we did here is for the Antarctic, for both solid and liquid discharge, so for iceberg calving and the subshelf melt, we use Schmidt et al. Dataset, which has it's basically based on other papers that are using some satellite estimates of these quantities. However, this time series they have a limited temporal coverage, and also, as you see, there is a very large temporal variability in them. And because we needed to have the coverage from 1940 to present day, and to make sure that we don't do anything crazy in the period that are not covered by satellites, basically we computed the mean annual runoff, and the value for it is 0.084 Sverdrups, which is actually quite similar to what Hiroyuki ended up applying in GRA 55 DO. I think in his case it was 0.087, but it was based on just 1 year of satellite measurements over Antarctica. And this runoff was applied for all years. We don't have seasonal cycle there. If we should, let us know. And we basically distributed it circum-Antarctically with making sure that the regional contributions are proportional to the climatological pattern. And for the Greenland solid discharge, we also used the Schmidt dataset, and for also based on satellites. And for the Greenland liquid discharge, we used Menkov dataset, which is based on the regional model for Greenland. And for the river runoff, we are using the simulations with hydrological model Camouflage that were forced by ERA5 reanalysis, and this data was produced to us by ECMWF. And from river runoff, we exclude the Greenland coastal runoff to avoid the double counting. Okay, so the next step, as I said, after doing the adjustment of the main variables, and this is something that I'm working on at the moment, is the global balance adjustment. So when we sum up all the components of the heat flux, so it's shortwave radiation, shortwave radiation, long-wave radiation, downward and upward, latent heat flux and sensible heat flux, and also the heat flux that comes from due to the latent heat flux is related to precipitation, and also heat flux related to river runoff, and some ice ocean heat fluxes as well. If we sum it all up, we basically need to come up with a factor that will allow us to make sure that the sum of all of these components of the heat flux, so that the Q net is basically corresponding to the historical ocean surface energy imbalance from IAP product. And this is what we are working on right now, to come up with this factor that will allow us to make sure that our Q net is basically what is actually being observed. And then a similar thing will have to be done for the freshwater, for the some factor that will be applied for the precipitation as well. Okay, I also wanted to quickly mention our proposed spin-up strategy for the OMIP runs. And here the diagram shows the standard OMIP protocol that is being used now, which is basically to run the model for 66 years from 1958 to 2023, which is the coverage of GRA 55 DO dataset, and do several cycles of this full forcing runs. And we propose instead to basically use 5 to 6 10-year segments at the beginning of the forcing data set to make sure that we reduce end of the cycle artifacts and also to reduce the computational time. Because if you run the model for this full period at the last decades, you start seeing the effects of the changes, climate change, global warming. So to get rid of it, we just propose to use the 10 years segments from the beginning of the forcing when we don't see these effects. And I wanted to stop here. So basically, and conclude that in terms of the adjustment, we have performed adjusting forcing variables. We created the runoff and discharge data sets. And now we are working on balancing global heat and freshwater budgets. And we are hoping to finish it soon and have the first version of data sets that we will be testing ourselves and also share with our project partners to test in GFDL and LANL models. And then based on the results of these tests, I'm sure something will come up and we will have to do some additional adjustments as well. And after we basically test it with CSM and with these other two models, hopefully we'll be able at some point in summer this year to share this data set for broader testing and evaluation among different groups and in other models. And if you have any feedback, if you do something outrageous, please let us know and let me know or email me or go and Fred. Thank you.
Once again, I think just one question for the sake of time, unless they're quick.
There's a poster out there too on this one.
Okay, and then there's posters at the break. So
Frank mentioned yesterday this work of comparing the humidity in the reanalyses to buoys, in that there is a systematic bias in the reanalyses. Are you modifying the reanalysis humidities based upon that?
We are aware of these biases and we talked to Frank before. For now, it's some of the things that I kind of keep in mind to kind of work on the next iterations. In theory, we can try to correct for these biases that we see in buoys, but the issue is that most of these buoys, they are in the tropical region, and it's a sparse observations, and they are covering tropics more than they cover the mid-latitudes. And basically, it's not very trivial to come up with a correction on the gridded data that would reflect all of this stuff. So it's something that we are aware of and we're thinking about, but we haven't done anything about it yet. But we will hopefully do something about it. Yeah.
Can I follow up afterwards? So our next speaker, get your talk set up. Thanks for that. So use this mic and rather.
Good job.
All right. Thank you.
All right, John.
Thanks.
So I'm a little embarrassed. I didn't realize that there was a ocean slide template. So I'm using the atmosphere slide template. So I apologize about that. So we're going to talk about the Turbo project, and has I think a nice acronym, and it means towards ultra high resolution community earth system modeling, CSM, with MOM6 and ocean biogeochemistry. And the overall goals is to enable MOM6 to efficiently utilize both CPU and GPU based systems, enable cutting edge oceanography at 1/12 and 1/36 degree global resolution, enable ocean eddy permitting coupled simulations, and we want to gain access to all leadership class systems that's being deployed by NSF or DOE. And so this is a 5-year cyber infrastructure for sustained scientific innovation, and this is a collaboration between CGD, CISL, Texas A&M, and of course GFDL. It should be noted that GFDL, between when we proposed this and when we received the GFDL, has started work on a directive-based approach. And so Sorry. So we're about a half a year into this. And I was going to mention the GFDL effort, and we view this as hopefully very collaborative and complementary. So the Turbo team, this is led by Gokhan. There's oceanography and community software support and CGD. Sizzle is the GPU enablement and optimization. And Texas A&M University has educational training component. So I wanted to set kind of one of the motivations for GPU enablement, if you haven't heard it already. So one of them is the NSF Horizon system. This will be a $250 million investment in Texas. Sometimes it's been in the budget, sometimes it hasn't been. Luckily, Ted Cruz is a senator in that state. It consists of almost 5,000 nodes of CPU and about 2,000 nodes of Grace Blackwell. I think the thing to keep in mind here is that the CPU cores, 900,000 of that, but in reality, if you write efficient code, it's about 22% of the capabilities in the CPU, and the other one is in the GPU. And so we really want the MOM community to not be limited to a fraction of a very large system. And of course, this is not the only system that's out there that's similarly has large GPU components. So some motivating oceanography use cases for this project. So idealized ocean-only simulations using Neverworld, forced ocean sea ice simulations at high resolution and also ultra high resolution, and that's the 136. I trip over that one, and then fully coupled simulations as well. And the last two really require leadership class computing. This is not going to be done at NCAR size systems. So the software approach. So Volve MOM6 code base so that it can efficiently utilize CPU and GPU based systems. And create an alternative for the flexible modeling system, FMS, that is GPU enabled. Again, GFDL has been working on this as well. Evaluate the viability of a pivot away from Fortran towards an alternative language approach for system modeling. We're going to talk about what that approach might be, and we haven't committed to anything yet, but we're going to make that decision in the second year of the project. At the end of the second year, excuse me. Why pivot away from Fortran? It's limited or lower quality vendor support versus C++ and Python. We kind of don't see this because we live in a Fortran world, and so and so what you tend to get is you get buggy support for Fortran on GPU, and so that means delayed access to new systems. So if you have a system that's deployed for 5 years and the first 2 or 3 are consumed by sorting through software issues, then that you miss out on that, right? Limited software tooling and workforce challenges associated with Fortran. So if not Fortran, then what? The one we're exploring is Amryx. It's a C++ productivity framework. It's for block structured AMR. And this was developed through the Exascale Computing Project. And it's used by a number of different application areas, combustion, astrophysics, cosmology, multi-flow, and accelerators. There's also, I should add on here, there's also regional model regional ocean modeling work being done by the DOE. Supports CPU and GPU efficiently. We've verified that. It's also Gordon Bell Prize is given every year for outstanding achievements in high performance computing, and it's been the foundation of one or maybe even more of those. It assumes a logically rectangular grid, provides a lot of infrastructure for I/O and message passing. So, and it grew up out of the idea of transitioning a code from Fortran to C++. So it provides a lot of infrastructure. And again, this provides more infrastructure than Cocos. Maybe you've heard of this as a language that's also being used in the Earth system modeling community. So talked about, all right, so here's the alternative to FMS, which we're calling TIM. So that's Turbo Infrastructure for MOM6. I guess it's a nested acronym. And so colored this. So the blue over here is basically Fortran code. And the yellow over here is C++ code. The dashed lines indicates if it exists or if it's or yet. And so there'll be interfaces into FMS, and then we're going to create an interface into TIM, and that'll be you can choose at compile time whether you use FMS or TIM, and so we want to have the same interface. And then there's this other thing called ProtoMOM-XX. I'll tell you what that is in a bit. We needed a name for it because it was a long string of words. So some of the relevant turbo software, Amrix exists, and it's based upon exascale kind of co-design or project. FMS, which Noah has written and exists for a long time. The FMS interface, so basically how MOM6 calls into FMS, and then the TIM interface, which is going to mimic that interface, but provide, but it's going to access TIM, which will be based upon Amrix C. And so you should be able to, the goal is to be able to switch over to this alternative infrastructure layer at compile time. ProtoMOM-XX. We didn't know what to call it. And so, but this is fundamentally a MOM6 C++ based prototype. And hope nobody takes offense by the name. We had to come up with something. Otherwise it doesn't fit on the slides. And so this is to be written, and again, it's a prototype, and its goal is to implement the double gyre test case. And so some of the timeline of the project. So let's see, we are here in the first halfway through the first year. The desire is to create ProtoMOM-XX and have it be visible to the community by the summer. I think that's optimistic, but still realistic, depending upon the day and how I feel. And then there's a decision point of kind of the future development. Do we go the C++ route? And the truth is, I colored these. It's got to be C++ plus Fortran, or do we stick with strictly Fortran? And that decision point is a year and a half away. Current status of the project: we've defined MOM6 configurations with increasing complexity. We've integrated existing MOM6 build with CMake. This was kind of challenging because it was really rather different approaches. We have a robust CI, and we actually have three of them. So what this does is you submit changes to that you want to apply to the source code, and then it goes in and automatically runs stuff, and it tells you if it works or not. MOM6 has this. It's a great idea. We're leveraging that, but we also have a CI for the interface code and also the C++ prototype with the ungainly name. We have unit tests for the interface, 18 of those so far. We have Google tests for the C++ prototype, 15 unit tests of those so far. We have an understanding of the modular dependencies, and we have a reduced complexity version of FMS too. So this is the very clear diagram that illustrates the module interdependencies within MOM, FMS, and other packages like Marble and CVMix. So the yellow stuff is what will be TIM or an option to link into TIM, and then there's the infrastructure that we're unit testing right now, which is in the red there. You can see it connecting it. So there is there's 230 different entry points into FMS, and so we're basically writing unit tests for each of those and verifying that you get the right answers regardless of the infrastructure layer you're tying into. ProtoMOM XX. So this is a small prototype that will solve the double gyre test case. It'll utilize a C++ driver at Amrex. So the notion is to see if you did go down the C++ route, what it would really look like, and show this to both the community and we want to have more experience with this ourselves. The group has a lot of experience with the challenges of Fortran with directive-based approaches, but we have less so with C++ productivity languages. So we're going to create this and kind of make it available and also to see what it looks like. So it'll be a partial implementation of TIM using Amrex. We don't have to do all 230 entry points, just 80. So that's a lot less scary. It'll have Fortran functions to test the multi-language code base. So it'll have parameterizations that are still in Fortran that are we believe will be pulled directly from the MOM6 repository, and also rewritten C++ functions to illustrate what it would look like. It'll be CPU and GPU enabled. I debated whether I put it on here, but I did anyway. It probably will include a static mesh refinement capability. You get mesh refinement capability as part of the Amrex. So it'll be there in the prototype as long as we don't do something stupid and mess it up. And so that's the goal, is to have this capability there. And then what we do with it, or what the community does with it, is that's an open question. But you could think of refining over areas of interest like I don't know, Chesapeake Bay or whatever inlets. LabC, that's right. You could get the LabC not to freeze over. All right, so questions. This is we went back and forth on logos, and so I put up the logo that Alper produced that nobody complained about. So I guess that's an executive decision.
We do have time for questions.
Yeah.
You said several times this sort of decision point at year 1.5. Is it really going to be a decision? I mean, what exactly, C++ or not C++?
It's
sticking with Fortran, which seems
it's staying with pure Fortran or moving towards C++ plus Fortran pieces.
So what would be an argument for staying with Fortran? What could be a potential argument for staying with Fortran?
User community is concerned about going to Fortran.
C++, concerned about
yes, that's correct. And so I think in my mind, I think it's pretty clear that we need to show this code to the user community. I'm a 35-year Fortran programmer, so I have a lot of, like, oh my gosh, this is new stuff. But I've looked at this code and it's like, oh, this isn't bad at all. This is very readable, and this is it looks a lot like what I've been programming for 30 years. So.
The Fortran plus C++ route, what does that look like? I mean, are you rewriting things that are already in MOM6? Are you just adding infrastructure around it?
So you can do both. So you'd have a C++ overarching layer, and then you could do the solid root C++, and you could attach it to a parameterization that's in Fortran, or various combinations thereof. And so you can link it together. We've done all the linkages and verified that it works. So the code would, if you would go the C++ route, the code would look like that for a while, because you can't simultaneously port hundreds of thousands of lines of Fortran, right? So you'd leave pieces in there that are Fortran. Yeah.
What happens with CIS if CIS is not ported to something that's GPU? Can you still get the gains from that?
I don't know what to do with the CIs. That's out of the scope of the project. That's a problem that this might create.
Maybe you should write another CSS side project.
Maybe it's another, it's another effort. That's correct.
I forget who the next speaker is, to be honest. I'm sorry. While we're transitioning speakers, I'll just say I like the snail logo, and also that Tim, is that a reference at all to Monty Python?
Keith asked that question too.
Yeah.
I don't think no. I think Alpha was Alpha was a creative one.
It wasn't a reference. Which one? So
The Tim.
Yeah,
Is Tim a Monty Python reference?
No. Oh, but it could. Cool. Good, go ahead, Mike.
Thanks, so my phone should be on. So Mike Levy, I'm a software engineer in the ocean section here at NCAR. When you talk about ocean diagnostics, like where we're at and where we're headed, two of the many projects I work on are kind of meeting in this talk. So a lot of the focus is going to be on Crocodile, which is the regional MOM6 project. And we're also going to talk a little bit about Cupid, which is the CSM unified post-processing and diagnostics. But as we'll see, where things stand, I'm going to talk about where we're at right now, and you can just see from the outline that it's pretty messy, and then we'll have a little bit of a discussion on where we're going. And this is an open question, so we'll be presenting an option, but asking for feedback on what we're thinking. Right, so like we saw in the last slide, things are just really fractured in the ocean diagnostics. So several years ago, Gustavo put together MOM6 tools. And he reached out to GFDL and asked about what they were doing for diagnostics, and they pointed them to some Python packages, and he brought them over to the NCAR machines and has been using them, and it's been really.
It's rubbing up and down on your shirt.
Sorry. It's just the handheld. Yeah, this will be okay. Oh, it's on the shirt and not on the thing. Okay, sorry. So Gustavo got diagnostics from GFDL. He ported them to the NCAR machines. It's been critical for CSM3 development that we have things that we can look at from the ocean model. And he started doing this probably before we had even really thought about the Cupid project as a whole, or maybe it was in step with it. Aiden, who's in the back, he added some notebooks to Cupid for the Crocodile project, like specifically looking at regional diagnostics. Kristen Crumhard has notebooks that she uses to look at ocean BGC. And I think these probably come from when we were still looking at POP output, and then she was able to port them to look at MOM output. So that also predates this Cupid effort. And then Cupid's here trying to make all of this available for CSM users. So I'll start with talking about what Cupid is. And I put like our vision statement, and really the goal of Cupid is to provide all of the tools in one place. And it always makes me think of this XKCD package about how, oh, there's too many standards, we need another standard, and then they just have one more standard floating around. But I don't think it's an accurate description of Cupid. Like Cupid isn't trying to replace anything. It's trying to be a framework that wraps around the existing packages and just makes the API a lot easier to use. Because right now, if you want to look at diagnostics from CSM3, you need to talk to Gustavo about how to use MOM6 tools. You need to talk to somebody in AMP about how to use the atmosphere diagnostic framework. You need to talk to somebody in the Polar group to get sea ice diagnostics. It'd be really nice if there's just a common API that could reach out and use these tools and then provide that output for you. So this is getting into the pretty picture phase of the talks. This is what output from Cupid looks like right now. You can see in the middle is what's actually the sidebar on the web page generated by Cupid, and it breaks things up by CSM component. And noticeable for the OMWG working group meeting, this meeting, is that ocean isn't listed in here because Cupid doesn't work with the ocean component yet. But it does provide some diagnostics from the atmosphere, the land, the sea ice, and the river components. I mentioned earlier, so MOM6 tools exists. It's built off of these CFDL scripts. I asked Gustavo for details, and he pointed me to MOM6 examples. And so I'm not actually sure which of these notebooks got incorporated in. But I mean, the main point is that we didn't try to recreate stuff from scratch. We started with what GFDL was already providing and brought it in. When you run MOM6 tools, you again get a sidebar that lets you look at a whole bunch of different ocean diagnostics, and I've highlighted some of the ones that keep coming up in the CSM3 development meetings. But you can see that there's a lot of ocean diagnostics available, and then this is like a really nice package to have and to run. On the Crocodile side, so I probably should have put that logo on like the first or second slide, but you get to see Dan's Crocodile in the middle of the talk instead. So these are the notebooks that Aiden put in. And so you guys notebooks that can look at the actual domain that you've created for this regional model. Like it gives you grid information. It gives you output in the region for a whole bunch of different fields. And then I had mentioned like we also have notebooks for diagnosing BGC output. And so you can get a table with a lot of important statistics. On the right, I have some stats about, like one of the big things we've been talking about is the oxygen minimum zone. That's something that actually looks a lot better in MOM than it did in POP. And so, that's on the right. Okay, and so we have these like 3 different sources of diagnostics plus the Cupid project. And so what are we going to do with it all? And our proposal is to start by unifying the global and regional diagnostics inside of MOM6 tools. So bring some of the functionality that Aiden has in notebooks that Cupid can run and get that into MOM6 tools. And then also bring in the BGC diagnostics. And once we have like kind of a single ocean diagnostic package in MOM6 tools, instead of being so fractured, remove the dependency on the NCAR computers and bring this in to Cupid. So like a rough timeline for that would be sometime next month. Like let's run MOM6 tools on a regional case and see what happens. We really have no idea what to expect. My guess is that we'll get some plots and we'll get some error messages. Spend the rest of the month kind of building a roadmap on how to get past those error messages and how to tie this all together. September of 2026, there's another Crocodile workshop. And our goal would be to have something, I guess, something better for that workshop. And then once we get past the workshop, look at the BGC diagnostics and the integration with Cupid. Yeah. So we get to the audience participation side of things. So these are kind of the questions that we're thinking about. How do we prioritize the steps that we just laid out? Like, is the proposal the right thing to do? What tools do you all look at when you're running regional Mom 6 and looking at the output? And then this is the point that I kind of threw in I didn't know where in the talk to put this, but like Cupid's really not designed for exploratory diagnostics. Like the purpose of Cupid is we have a set of standard diagnostics that we want to run to look at, and that doesn't really help do new science and look at new things. Is that something that we should figure out how to support, or is it okay to have people do the exploratory diagnostics in their own way, and then when they come up with something they want to look at, figure out how to shoehorn it into the existing framework? So yeah, I'm happy to talk about it during the break, or we can email about it or set something up. I think we probably have like 5 minutes left in this time slot also. So thank you.
We do have 5 minutes. This is a 15-minute time slot. And the next talk starts at 9:45. So plenty of time for questions. Alistair.
Yeah, hi, Mike. It's actually partly a comment. One reason why it's has been so hard to share scripts for ocean models is that we have this tendency to use these weird grids like tripolar grids. So something that's happened here is, and it's partly the result of how things worked in CMIP, is that we've started post-processing all of our output to 1x1 grids. And that has made it a lot easier just to have simple analysis scripts, which everybody can then use. And in particular, when you're comparing to gridded products like, World Ocean Atlas or Reynolds SST and so on. So, that's as part of our workflow now, we basically have a standard post-processing that just maps to the same standard grid. And then anybody can write a three-line script that can be used by anybody else. So that's one thing which I felt has been hard for sharing between groups, because we all have different grids. Some people use bipolar, tripolar, everyone has different choices about where to do things. And so it's been very hard to make our analyses work uniformly on other people's models.
Yeah, so that's a good point. And Cupid does have rewording in its post-processing toolkit. And so, that's something that we could definitely set up so that CSM remaps to a 1x1 grid, like just by default, all the ocean model gets remapped to a 1x1 grid. And then we'll have that for looking at some fields, and the native grid's still available for fluxes and conserved fields.
Mom6 Tools doesn't currently do that, right? No. All right, in the back, and then Justin.
This is kind of in reply to Alistair's comment. So, yeah, I think it would be great if we could separate development of tools for Mom6 and also CESM so that we could collaborate with GFDL and access folks and stuff. I guess, Alistair, you're talking about interpolating to a 1x1 degree grid. Do you have any thoughts on how that would translate to a regional picture where, resolutions and grids are all over the place?
Yeah, whole different problems. I actually don't know what to suggest there. Sorry. Obviously, a standard 1x1 grid is pretty not useful for the regional models because you're looking at finer details and you're 100 kilometers. So I don't know the answer to that one. But you do have the advantage that it's mostly a rectangular domain, at least logically, right? So the mapping isn't too expensive. The problem for the global grids is that people would have folds in different places, and it gets very complicated to do a global grid. I'm not saying it's easy for coastal people, but yeah, we should perhaps talk with the CEFI group here and find out what their plans are for this.
Okay, thanks.
Justin?
Mike, I had a question from the previous slide, and you were talking about using Mom6 tools on regional case. How does the Crocodile work fit into that? Because you mentioned that Aidan and others have been doing scripts for that.
Yeah, so sometime next month, I'll talk to Manish and ask him to provide me an output, and then I'll talk to Gustavo and ask him to point Mom6 tools output to that case, and then we'll see what happens. And, yeah.
Got a couple extra minutes. Well, if there's no further questions, let's see if, well,
Yeah,
you got
just
one?
a comment. I think it's important that whatever we come up with, it is expandable. So like a new user will come and say, I can see that AMOC is already computed this time series of ACC transport, but I want you to do something else. How do I start? And in Mom6 tools, there's every time I do a script, I do a companion notebook, and there's like, I wouldn't call APIs, but no software engineer APIs ways of getting the data and loading the SCDF and things like that. I think it's important that whatever we do through Cupid, Mom6 tools, like that is there, like that. You know, if someone comes and wants to do something new, it is that there is how to start.
Yeah, so I mean, that's kind of this exploratory.
Yeah, I mean, in addition to being expendable, because that was the sort of criticism of the previous packages that we ended up with, is another important thing is publication quality plots coming out of the thing, because that was another problem in the past. We had the packages, but people didn't want to use them because the end result was not publication quality or not easily customizable. So I think, and that was the failure of the previous ones. So I don't know how, in order to get more buy-in, we need to make sure that Cupid actually produces easily customizable publication quality plots at the end of the day.
Yeah, and that was something that was like on the roadmap, like kind of from day one, and it hasn't been talked about much recently because we've been just focused on getting diagnostics out. But that's a good point. That is something that we want to make sure we do.
Output like companion NetCDFs from the data you're plotting?
So Mom6 tools generates NetCDFs of fields. Cupid in its post-processing generates time series files, but that doesn't really dump the intermediate NetCDF of computations. It keeps things in memory.
Yeah, so that goes to Gokhan's point. Doing sometimes the better quality takes longer computer-wise, and it already takes, depending on the length of the couple run, for example, 10, 20 minutes to run the diagnostics. And if you have make better figures, it will take it longer. So the approach is I save the NetCDF files, intermediate NetCDF files. If you want to do better plots, you can change the script to use ArtoPython, something more robust.
All right, we're over time. I want to have our last speaker not be late, so we can keep talking. Sean. So we'll put that on.
Okay. Okay, so I think I'm fine. I'm Shani Wang from Xiamen University. This is a recent model development work that we did together with Robert and Ranka and Xiao, my student Xiao, who did most of the coding to simulate methane in the global ocean. So I think I don't need to mention too much about the importance of methane, and it's a great important greenhouse gas, which has strong warming potential. In ocean is an important natural source of methane to the atmosphere, but we still have large uncertainties in terms of the overall amount and the spatial distribution from ocean methane emission. And also we state party on methane simulation, probably no global methane simulation yet. So that's why we want to work on that. And so in terms of methane cycle in the ocean, there are I'm listing major sources and sinks. And unlike other physical processes, we don't have equations ready. So the main process in this study was to figure out what's the proper way to represent those sources and sinks. And traditionally, we think the most important source of methane in the ocean coming from the anaerobic production in sediments by archaea, which use the low molecular weight compound to break down the compound into methane below the methane sulfate transition zone. And then also another important source will be geological methane sources, including the methane hydrates and also the seepage. And then later people observed methane production in aerobic condition and sunlight condition. And so there is also a methane paradox that I'm going to talk about next slide. And in terms of sinks, most of the methane produced in the sediments can be consumed actually within this sulfate methane transition zone there. And then also in the water column, there is another removal pathway through the aerobic oxidation of methane involved by microbes. And the other sink would be the air-sea exchange. And the methane paradox was the methane production in sunlight oxide environment, which was realized like in the past, mainly observed in the past 20 years also. And there have been several mechanisms proposed to explain this methane production in the oxide condition, but still we have a lot of unknowns in terms of exactly what's the mechanism mainly produce methane in the sunlight water. And so there have been proposed hypotheses saying the methane probably produced in some anaerobic conditions, such like the guts of fish or zooplankton or the small particle within the small particle. But there's have been recent discovery on the methane production through the microbial degradation of DOP, so dissolved organic phosphorus. And so that's this pathway here. Okay. So basically, we are using this as our mechanism that we are going to take. So based on the major sources and sinks, that's the major terms we want to represent in the model to really calculate the dynamics of methane in the ocean. And first of all, I'm going to talk about different source terms here. And the first one will be the aerobic methane production within the water column. And we are taking the hypothesis saying the methane is mainly produced by the remobilization of DOP, in mainly the methylphosphonates, which is a small fraction of phosphonates in DOP. And then here, the first several terms, basically the fraction of phosphonates in semi-labile DOP, and also the fraction of MPN. And then the based on measurements, they have like is determined only certain amount of DOP remobilization can be enough to support the production of methane within the water column. That's also that's the third term. In the RC2P here is represent the stoichiometry ratio between carbon and phosphorus in organic phosphate. And then the second source term will be the anaerobic methane production within the sediments. And first of all, we consider the redox ladder of methane, like different compounds within the sediments. and then realized it's probably not the best way for us to do that because the marble doesn't have all these sulfate in all different compounds within the sediments. So we decided to take the proposed mechanism, suggesting the methane production probably due to the archaea breaking down the like small molecule, organic molecule like acetic acid. And there have been studies trying to get the fraction of how many organic remineralization can contribute to the methane production within the anaerobic sediments. And that's the first factor F here representing. And then the second term, actually, because we want to compound the depth of sulfate methane transition zone, if we have a really thick SMT, then the methane cannot really reach the surface of sediments and cannot really diffuse out from the sediments. And then there have been some estimates for the distribution of SMT in the global ocean and also observation in terms of flux of methane and sulfate within the sediments. But since our model do not have the same topography, topography of as the observation, so we sort of like did some area weighted scalar there. And then the part will be, we are using the other remaining term instead of the POC sinking to the seafloor, because when POC sink to the seafloor, it can be, there can be denitrification and burial, and which cannot really contribute to this production. So we are using the other remain, which already subtract the denitrification term from this POC to floor. And the figure on the bottom left showing the distribution of other remains simulated by marble, and on the right showing the averaged anaerobic production of methane within the sediments. And of course, we don't really have the sedimentary module in marble, and this is basically, we estimate the methane production within the sediments. And then we need to consider the removal process, which is the sink term. I'm going to talk about it later. And then also the bubble-driven source of methane. So for this part, we know there have been some estimates for the methane distribution, methane source from hydrates and also the seepage. If the seepage located in really deep ocean, then probably the methane cannot reach surface. So we ignore that contribution and mainly consider the coastal sources. And we did this source based on the study from Weber, in which I used previous estimates suggesting the methane emission from seepage and hydrates about 18 to 48 teragram methane per year, and we are using the 18 teragram per year for now. And you can see the basically we distribute this emission evenly in water shallower than 200 meter, and then the lower right shows the distribution of surface methane. Sorry, it's so blurry. And then we'll be going to the removal terms. The sink term, the first one will be representing the anaerobic oxidation of methane within the sediments. Like I said, we don't really have sedimentary module yet, but there have been some estimates suggesting methane produced beneath SMT can only largely consume the within SMT, and only like 10 to 20% can get out of sediments. So we are using a simple fraction here, and just to compound the AOM in the sediments. And the second removal term will be the oxidation in water column. And we basically collect all the observed methane removal rate and from different wells in the global ocean, and try to fit different curves that probably can fit our need. And we tried 8 different equations, and here is the curve fitting, and we found about 4 of them probably fit better. And then we did further test with this 8 equation, including the Hale equation, Mechanism-Menten, and double Mechanism-Menten exponential equation. And then here, so we need to decide which equation to use for the water column removal. And the idea would be have a faster removal rate when the methane concentration is really high, and low removal rate when the methane concentration is lower. And then there have been some previous estimates for how much methane can come out from ocean from different sources, and we want to make sure our simulated results fall in the previous estimated range. And also there have been some observation-based estimates for how much methane coming out of open ocean. Of course, most methane is emitted from coastal regions, but there have been estimates based on observations from Pacific and Atlantic stations, and suggesting there will be 0.4 teragram per year in from open ocean, and that probably mainly contribute from the water column production in the aerobic condition. And like you said, we consider 3 different sources: the seepage flux and diffusive flux, which is the anaerobic methane production within the sediments, and also the water column aerobic methane production. And so we test different functions, and in our results suggest Hale function probably fits our need better and fits all the observation data better. And that's the one we decided to use for the water column removal. And the last removal, the last sync term will be the IRC flux. That is quite standard. And we are using the parameters from the 2014 Smith number. Okay. And we did some sensitivity tests to see how sensitive the simulated methane emission to different choice of parameter values. And so based on our the equations or the source terms, there can be some variation in, for example, the aerobic methane production within the water column in terms of the fraction of phosphonates, and also the fraction of how much the methyl phosphonates can recycle and produce methane within this semi-labile DOP pool. And we test different fractions, and of course then VC is not very sensitive, probably because this is a really small terms in terms of the overall methane emission. And then we try the anaerobic production of methane within the sediments. So previous, well, in theory, beneath within the sulfate methane transition zone, there should be a stoichiometry of sulfate and methane 1-to-1 stoichiometry ratio. But actually, the observation suggests more like 1.4 to 1. That's the one we used in previous tests, but we also tried 1-to-1 ratio in our test, and that's the middle part here. And also probably didn't make big change. And in terms of the removal term of within the sediments, since we can't do much on that because we don't really have an explicit sediment module, so we try different fractions of how much methane gets removed within the sediments. And that gave us some variation between 7.2 to 8.4. And the largest variation actually coming from the estimates for how much coming from bubble-driven sources, including the seepage and methane hydrates emission. So previous estimates suggesting like the hydrates emit provide like 18 to 48 teragram methane to seafloor at seafloor. So we try different numbers. In both the top row, we shows the average water column average methane concentration, removal rate, and the total RC methane emission. That give us a 7.9. But you see, if we use a higher methane from the bubble driven, like the Iblex methane emissions at the seafloor, we get 13.4, but still that fall in previous estimates. So the previous estimates suggest the methane, overall methane emission range from 5 to 25 teragram per year. And here I'm showing you the contribution from different sources. So the top left showing the contribution of if we run water column methane production alone, how much methane, that's the average methane concentration. And note that color bar is really small. I'm sorry, it became so blurry here. Is the top value is 4 teragram, 4 nanomole here. And the other 3 panels shows the color bar up to 100. Okay, and so the top right shows the methane production from the anaerobic methane emission alone, and then the lower left shows the geological methane sources, contribution of geological methane sources, including the seepage and hydrates emission, and that's the lower right shows the overall. And as you can see, probably still the methane from hydrates and seepage probably constitutes the largest source in determining the large pattern of methane emission in the ocean. And so basically that's all. And it seems we can still get an okay agreement between our simulated methane distribution with previous momentum observation concentration and the simulated methane emission ranging from 7.2 to 13.4, also for in previous estimates. And we think the magnitude of geological source probably really is the largest uncertainty in terms of the simulated ocean methane emission. So that's all. Thank you.
For a quick question, if there is one before we go to the break. All right, well, we're right on time. I think if you do have questions, I invite you to talk to Sean Lin during the break. We come back from break at 10:30, so 25 minutes from now, back in this room. That's all there is to say, so see you then.
Okay, it's 2 minutes past the time to get started. We are not doing a very good job in keeping time, but let's see everybody else here. All right, so this is the second session of this morning, and it's my pleasure to introduce you to Ryan Du. And Ryan will talk about quantifying wave groups' contributions to variability in surface wave properties. Please take it away.
Thank you. Turn it on. Oh, that works. Amazing. Okay, yeah. Thank you for giving me the opportunities to talk here. Right, I'm at Mines, so not too far away, and there I'm a postdoc working with Bia Villas-Boas. Then I also work with MoME, someone here, and then that's also the rest of the people. So this is a SWOT project. So I'm going to tell you a little bit about SWOT, but hopefully I'll relate to you something that this could tell us about models as well. Okay, so SWOT, if you have heard, is a satellite that is new-ish now, right? And a observed sea surface height, which then you can use geography to calculate current, which is the one on the right. There's also a wind speed product, but I'm going to focus on the significant wave height product, which is the one on the bottom. So this is the SWOT geometry. Whoopsies, I should not be touching that. Right, and right, it has 2 swath and nothing in the nadir. It's a 2 kilometer by 2 kilometer resolution observation of SWH, which is awesome and is unexpected. Before SWOT was launched, they didn't expect that we could do this. So it's exciting to be working on this. So what the first thing you could see right, on the two, there's a comparison. The background is a model output. So it's a wave watch ran without current and with current. So ocean current refracting the waves. And clearly comparing to SWOT, current definitely affect surface waves. Cool. Right. So then, but if you look in more carefully, there's pixel level variabilities that is not present in the model, but in the observation. I think it's harder to see now on the a little bit pixel of the screen, but here is a zoomed in. So this is an even more groupy case where that's the SWOT geometry. You zoom in to a little section. So this is just that, the black part over there, right? And then even sometimes when the group is big enough in this wavelength and magnitude, you can even see it in the SSH observation, which is what SWOT mostly made for, but you can see groups, you can see waves doing that. But you, right, there are pixel level kind of variabilities in the SWH product, looks somewhat like noisy things, but they are actually real signals, at least in some extent, right? Because you can see the actual SSH observation over here, and it's real. It's wave groups. It's basically wave packets that are large or small, and it seems like SWOT can see them because it's in 2 kilometer resolution. This can pose problems for validations of this data set. So over here is another SWOT swath, right? And first you can see there's eddy there. This is in the SWH, right? But you can definitely see some wave current interactions. But if you look in detail, easy to miss. There's a line also on the right swath with white borders. That's an independent observation called MASS. So this is a plane with a LiDAR hitched on the bottom, and it observes SSH in extremely high resolutions. But then what is that SWH? Without just calculating the standard deviation of the SSH observation. So what they do, right, is they chunk the data in 2 kilometers. It's 400 meter in wide. This is the plane, and then 2 kilometers, and then they also have independent observation of significant wave height. And if you plot the two on top of each other, they look pretty good, right? That's why it's easy to miss this line in the 2D plot. But then there's also a lot of variabilities, and this is because of groups that pose kind of challenges to validate this SWH product in basic sub-mesoscale resolutions, because group is kind of dominating. So the purpose of this study, which is the first step into understanding this, is to just model what the wave group would look like in sub-mesoscale resolution observation. I'm going to tell you the few key ingredients, right? So the first one is that group, the one that will show up in observations, it depends on the size of your observational window or averaging window. All right, so for MASS, right, you can see the 3 plots. There's clearly difference in how much pixel level variabilities it's showing. Right, the black curve has the most, and that's because that's MASS, that's the plane. It has limited swath width, and they chunk it in 2 kilometers. That's the choice they made to plot this particular curve, right? You can make other choices. There are interesting questions on what you could do. But anyway, so in this case, it's 2 kilometers by 400 meters. Then SWOT, they have 2 products. They have 2 by 2 kilometer product, and they have a 5 by 5 kilometer product. And clearly, the 5 by 5 kilometer has averaged the most. It seems like it has the least pixel level high frequency variabilities that you see in the data. Right, which makes sense because wave group of a particular size, the more you average, the more up and downs that you average over each grid, right? And then the variabilities get smoothed over. So to model wave groups by itself, we can approach this cleanly by just isolating what wave group is, and I'm particularly focusing on the linear mechanism. So what we do, right, is take a realistic surface wave spectrum. So this is from C-dip buoy. This is in Southern California. And in this particular case, the wave is coming from the Southern Ocean. So it has propagated all the way across the equator. And because this has gone a while, it's very swell-like. And the spectrum is very tight, very peaky. That's what they call, right? And if I just take the spectrum, generate an SSH field, homogeneous in the statistics as a Gaussian random field, it naturally forms groups, right? You can see in your eyes there are regions that are ups and downs. So that's basically the groups and modeling. And a useful tool to study this is you can calculate basically the envelope of the group, which is like its instantaneous magnitude. So this would be our version of the unsmoothed envelope, unsmooth version of SWH, right? You do this by using a Ritz transform, which is the extension of the Hilbert transform method that everybody has been using for a while, right? So that's what a wave group is. The last plot, it's kind of some blobs that is just naturally formed, not due to any differences in statistics across the domain, but just by random phase additions of waves. So what actually matters for the size of the waves, I have two examples here, the one that we have seen, and then another one at Ocean Station Papa, where it's wind-driven sea. So this is shorter period sea, but more importantly, that is broader, it's less peaky. The spectrum is a big blob. And when the spectrum is blobbier, the wave group is smaller. And right in the last picture, now I've added basically what I would do if I grid the envelope into a 2 by 2 kilometer product, just like what SWAT would do, right? For a wind sea, there are barely any variabilities due to wave groups, but for swell, there are quite a bit, right? And we can characterize this by using this Heisenberg inequality, which is the same as the one for the uncertainty principle, but there's no quantum here. It's just consequences of Fourier transform. It's the second moment for the autocorrelation function times the second moment of the spectrum of the envelope must be bigger than a constant. So that means if your spectrum is peaky, so it's very tight, right? This second moment is small. That means your wave group is big. So this is the second moment in space. Right, and in 2D, there's some more details now in some of this works for each angle. So you can see the spectrum has a bigger second moment in this direction. That means the group is smaller in that direction. Right, makes sense. Okay, so I'm gonna blow through some math details because it's a short talk. Right, basically what then we would do, given all this information, we need to know about what the window size and shape is, and we need to know what the group size and shape is. And then we can put them together because you're observing the group using a window, right? What you could do is approximate both of them as a Gaussian, and then averaging is basically a convolution, which is in the product in a spectral space. And then because everything is Gaussian, I can calculate everything explicitly. So I then eventually get a formula, no numerical integration involved, right, of the variance of the observed HS, which is the target we're looking for. Cool. So then we can apply this to the thing we want, which is SWAT, right? I've brought this figure back. The line plot is exactly what I've shown you a few slides ago, but now I have a few candlestick bars where the candlestick is one standard deviation of the HS due to only wave groups. So what the conclusion I want you to draw is that this crazy pixel level up and down variabilities that you see in this line plots kind of matches what would happen just by wave groups, right? So it seems like in this particular instance, right, that pixel level variabilities in mass and in the two SWAT products are probably actually, at least in a large part of it, due to wave groups. So this is kind of real signal that it's actually measuring, and not because of noise, even though it kind of looks like it. but SWAT do have noise. So this is another case that is less pretty. So this time the plane flew like this. This is like 0, it goes, and then it went, I think then it went other way around, but we're focusing on like 0 on the edge of the SWAT swath, right? And so the color is the same. It seems like for mass, the pixel level variabilities really still matches the candlestick because the plane doesn't care about where SWAT is. It's independent, right? But for SWAT, first there's a big error in the mean. We kind of know why that is, and there's a existing fix by by Alejandro Bohe, who made this product. So perhaps there will be an existing fix that already would fix that. But what that won't fix is this variability problem. That it seems like SWAT, in this case, if you compare the variabilities to the one that is in the candlestick, there's way too much. And this is contributed to SWAT noise. It's basically noise in the SWH product. And this is also to be expected because it is harder to get the SWH out of what SWAT sees, the electromagnetic signal, at the SWAT edge. So you can read Alejandro's theory paper on how this data is produced. We kind of expect that as well. But to be able to actually say this is noise, we need to know what wave group would look like, right? So we can only draw this conclusion by making this plot and say, yikes, that looks like a lot of variabilities compared to what wave group would give you. So that's the point of the modeling study. Cool. So this is the last slide where I know I'm talking to modelers, so I kind of want to go beyond SWAT for a little bit, right? So the bigger conclusion that is that we can draw is wave group contribute to some mesoscale variabilities in wave properties. I only talk about significant wave height, but it's the same for Stokes drift or wave spectra. And this work is a model for basically how much error bars that you can expect, right? One question we could ask, right, is we have done 10 years of studies of surface wave refracted by currents, right? But once now we look at observations, and right, it's hard to tell what the current-driven variability is now in the submesoscale because the wave that's most affected by currents is the swelly ones, and they're the most groupy ones. So it's kind of the red signal in SWH because of currents eventually get overwhelmed by the group signal. Right, and this is now kind of thinking about, right, this data model comparison is WaveWatch, because it's a phase average model, doesn't actually have wave groups. I mean, that's by design. But then when we run it at some mesoscale resolutions, the reality doesn't actually look like what WaveWatch does, because it does have a lot of wave groups, because the reality is one instance of the statistics, right? So I'm not kind of drawing any conclusions here, and right, but I kind of invite people to think about and talk to me about what we should think on WaveWatch running the submesoscale. What does that even mean anymore? Right, so data model comparisons and data comparisons need to take care of basically wave group in mind, because that's what reality looks like. And lastly, I'm kind of throwing this out there also as an invitation for discussion, because I think most of the room knows more about this than me, is we're putting surface wave properties in parameterizations now, right? But in reality, what a wave group, what wave actually looks like, it looks like this, right? So we're kind of putting HS that's being spit out by models or climatology, right? But the waves don't necessarily look like that in reality. And I learned a lot yesterday about wave-ice interaction, so I added this little thing late yesterday. This is kind of a thresholdy type particular parameterization, and that's kind of interesting to think about what wave group would do in that particular situation. Cool, that's all.
we have time for 2 quick questions. I have one. Can you, based on the surface wave height, can you then extrapolate how would that affect, for example, the Stokes velocity, which is what we use in the parameterization?
Right. So the wave group, right, where I only talk about in SWH, is intimately related on the basically the uncertainty in observing wave spectra. Right. You have to, even for the frequency spectra, you have to decide on the length that you're calculating your Fourier transform, and right, and then there's a tube of uncertainty every time you calculate the spectrum. So really, they are all one and the same. The variability for SWH is just basically the integral of that uncertainty, but Stokes drift is just a different integral of the wave spectrum. So you can just do the same thing. Right. So they're all calculatable. It's just somebody have to.
Yeah, because for the parameterization, that's what we're using now.
Right.
We don't use wave height at all.
Cool. Yeah. Okay.
Like wave theory is probably used as a very well or not, right? Because if you're like a lower frequency and like a longer period, and that's exactly what you see when you have swell. And then you have like a very narrow band in the spectrum, and then when you have wind speed, it should be a little more spread. And I guess, yeah, I haven't thought really about it, but we need to like assess how broad is this frequency band to really say something about it.
Yeah. So the basically the next thing to do, which is useful for models and for SWOT, is to do some kind of topologies on what this actually look like. Right? It will be important for the wave current interaction one question as well, and just as an error bar for what basically SWOT sees, but also for broader questions of what any of this actually means.
Let's take Ryan one more time. Okay, the next talk is by Kate Bowden and is on the effects of backscatter parameterization in MOM6 on global ensemble-based data assimilation. Please take it away.
Good. Okay. Oh, yeah, that makes sense. Okay, so I'm a PhD student at CU in the Applied Math Department, and I'm going to talk about the effects of backscatter parameterization that we've been talking about in these last 2 days on MOM6 for global ensemble-based data assimilation. So we haven't really talked a lot about data assimilation, so why not motivate a little bit why data assimilation might be useful for modeling in the ocean. And let's say we want to do subseasonal to decadal predictions, and we need good initial conditions to get good predictions, but maybe we don't have those, so we could do a pre-data assimilation on some initial conditions. So we have an ensemble and then incorporate real observations so that we can constrain the state. So how we do this, let's say you have a forecast. Here I'm showing 4 MOM6 sea surface temperature forecasts, and then we have our rubber ducky observing system on the ocean. And we're combining these 2 imperfect dynamical forecasts with imperfect observation for an improved update to the state. I've been able to actually do this with MOM6 and DART, the data assimilation research testbed here at NCAR. And you can see here for this is January 5th. If you have a forecast mean in the top and I'm subtracting the truth, you see a lot of bias in the model, but then the analysis, which is the data assimilation update, you've reduced that bias, especially in locations where we have observations. Not only do we improve the mean, we also improve uncertainty. So now we move beyond rubber duckies to like actual observations, mooring, APB, floats, XBT. These are the observation locations, but everything I've done is synthetic up till now. And you can really see that the standard deviation, the spread in your ensemble is small around your observations, whereas down in the Antarctic, where you have there's less observations, your ensemble spread is still pretty large. So I want to talk though about what is happening with the eNKF and when it's well behaved versus not, for why the backscatter parameterization might be helpful for us. So in this case, I have some chaotic dynamics. So small changes in my initial condition lead to very different outcomes. But we start with an ensemble. Here I have 3 ensemble members. MOM6 forecasts us forward in time. An observation becomes available, and the eNKF increments our forecast to an analysis that is now closer to what truth is. And we can do this again. So MOM6 forecasts forward in time, observation becomes available, eNKF increments us up, and so on and so forth. So now we see that the actual ensemble is much closer to the truth than if we had just let the chaotic dynamics run away on their own. But this is well-behaved eNKF. If I, am I going the wrong way? Okay, there we go. But if I go quickly between the well-behaved and the under-dispersed ensemble, what I'm trying to demonstrate here is that if you don't have enough variability in your ensemble to begin with, you might not be trusting your observation despite the fact that it is actually trying to help you get towards your truth. So I gave one little equation here at the top where the change in the state that's happening from your eNKF is proportional to the variance in the forecast over the total variance between the forecast and the observation. So if your variance forecast goes to 0, let's say worst case scenario, and all your ensemble members collapse, then you wouldn't get any update to your state despite the fact that that observation at T3 is showing you something closer to the truth. We have a fix for this. The DART team does adaptive inflation spatially and temporally. So this will inflate if the observation represented here by Y is much larger than your ensemble mean, and larger in the sense that if some of the variances cannot account for that difference, then we apply inflation. So for January 10th here, I'm showing pretty large inflation factors because we still have some model bias, and so we need to inflate the ensemble. But by March 11th, we've run data assimilation for 2 months. Every 5 days, we've reduced the bias. We no longer need to inflate the ensemble as much to account for the uncertainty. But we're not really addressing the underlying issue when we're doing this, which is we have the lack of model variability in our ensemble. So inflation addresses a fundamental limitation of coarse resolution models where we have insufficient variability due to subgrid scale processes. But we already know that MOM6 includes a backscatter parameterization designed to represent the impact of eddies and other variability. And we've seen in other talks that it does increase variability in our simulations. So could we improve not only the model dynamics, but also ensemble-based data assimilation with these backscatter schemes? Which leads me finally to the research question we've been looking at, which is to what extent can the physically based backscatter parameterizations within MOM6 reduce or replace the need for covariance inflation in ensemble data assimilation? It's worthwhile to at least speak briefly to the backscatter parameterizations that we've talked about. There's 3: stochastic GM plus E, stochastic equation of state, and deterministic Leith plus E. This image has actually already been shown, but I'm going to show it again because you can see the sea surface temperature standard deviation for temporally here with observations. So we know that we have variation that doesn't exist in our control models, which is what I'm showing in the middle. Oh yeah, you can see that in the middle, and I'm highlighting in the Atlantic there off the coast of Africa. But when we add these backscatter schemes, we go from the blue to the red, so we've increased the variability. And so we know that these are improvements to the model to begin with, but we want to investigate whether or not those improvements also help us with the data assimilation. So like two birds, 1 backscatter, 3 backscatters, I guess, technically. Anyway, so how did I set this up? I've spent the last 8 months getting this thing to go. And I'm using nominal 2/3 degrees, so pretty coarse G-case ocean ice. I have an ensemble size of 40 members, 75 vertical layers, Z star. And I'm assimilating every 5 days. I have salinity and temperature observations. These are synthetically generated, but I am at least interpolating onto the World Ocean Database to have that realistic component. I have 250,000 observations every day that I'm assimilating, and I'm not just updating salinity and temperature, but also horizontal velocity, U and V. I'm using localization because I have a small ensemble and spurious correlations can be a problem with ensemble DA, and I am using inflation adaptive on the prior only to account for potential model biases. We have 4 experiments that we're running to look at this for 1 full year, 2011. So we spin up for 53 years, and then I'm gonna run this thing for a year. I'm highlighting in yellow what I've actually been able to complete, which is using the control case to generate my synthetic obs. So I generate a truth run, get some synthetic obs. That's what's the observation source is. And then the MOM6 configuration, I'm gonna compare a control with a backscatter. And then I can do the same thing using the backscatter MOM6 to generate synthetic obs, which I have, we just haven't run the experiments yet. Because this is a working group, and it's maybe useful to talk about issues, one of the issues that we recently ran into is that DART, the ENKF, makes Gaussian assumptions, and it can have non-physical increments. So this became a problem with us with interacting with SEISS in the ICE model. Here I'm showing you the forecast mean for August 18th. So you have some violations of a theoretical freezing. My theoretical freezing here is just a linear relationship based on salinity. But DART is gonna, you can even see the scale here is going all the way down to -3.5. It doesn't know or care about those things. And so you can get non-physical increments. And so I have you have to account for this by updating your restart files. Kind of a pain, but we don't personally care too much about what's happening in this region, but it is an interesting problem. So I'm putting it up here, but I just applied a fix. Oh, I think I have it on the next slide. Yeah, so this is my quote unquote fix, post-process the restart files using a linear approximation for the freezing temperature based on salinity. And I'm adding some epsilon just to make sure nothing gets annoying because I'm tired of seeing the thermodynamic errors in my SEISS files. And that worked. So that was really nice. And now I can actually show you some simulations for 1 year. If I hit this again, oh yeah, here we go. So on these, again, we are simulating only control observations. On the left, you're looking at MOM6 control, so there's no backscatter there. And on the right, you're looking at a backscatter package. So all 3 of our backscatter, stochastic and deterministic. It looks pretty bad in the Atlantic. You can see it going crazy over there. It's kind of like a little dance party. So the increments are obviously non-physical and doing something weird. We think that one of this could be because correlation lengths are smaller with the backscatter, right? We're adding more variability. There's not as wide of correlation spatially. Let's let it, okay, yeah. So they're pretty to watch, but these aren't necessarily the results that we're happy with for the backscatter case as of now. So we started to investigate this a little bit more, looking at the correlation structure. So on the left here, you're looking for the backscatter case at a point here in the Atlantic, sea surface temperature, spatial correlation, and I'm plotting on top the localization radius. So you can certainly see that there's strong correlation right around the point that I'm centered at, but that you have a lot of spurious correlations happening outside of that point, which could be leading to bad increments using the ENKF. Vertically, we are not using any vertical localization currently, but yeah, it drops off pretty quickly and then gets what looks like pretty spurious also. So maybe adding some vertical localization could improve our results. But I will make the comment that if you look at the control correlation structure, vertically it's actually pretty similar. I quickly go back and forth. But we did see fine behavior with the control case. But it's also, you can see the control does certainly have larger correlation structure. It's much smoother. And so that localization may be appropriate for that case, whereas the stochastic case, maybe we need to cut it in half or something. This has been a long project of getting this thing to go. So I have some documentation on that if anyone else is interested in running MOM6 with Dart. So you can check out my GitHub pages. So I have case setup and runs, input configurations for Dart that you might want to use, tips for viewing results, restarting a failed case, because certainly your cases are going to fail, and ongoing updates. I would definitely want to add to this perfect model obs and using the World Ocean Database. I think that also could be helpful for people, but I'm open to feedback if people want to know something about how this project got going. I also want to thank everyone from the Dart team. Also, I think Enrico's on this call. I see him. Enrico was also really helpful for this. But Moha, Jeff, Dan, Helen, Kevin, Molly, and of course, Ian, my advisor. this project pretty much only exists because of them. So that's really great. Also, Fred, who's here, was a good consultant in the beginning too. So that's all I have.
We have 5 minutes for questions.
Thank you for the very nice talk. You were criticizing the behavior in the Atlantic with the spurious variability, but I thought the Pacific and the equatorial tropical instability waves look better, and they seem to be enhanced relative to the control. So maybe not all is
lost. Yeah, well, Ian and I were also talking about this. Can I play it again? How do I play it again? No. There we go. Might as well just play it while we're talking. Yeah, so you're talking in the Pacific along the equator is looking better.
Well, it did look when I saw it the first time.
Yeah, sure. We can watch it again. I haven't plotted RMSE yet. So we haven't looked at all the metrics to really evaluate performance here. But that certainly that's bad. But maybe we are getting some benefits there that we'll be able to see in other ways. We were thinking about turning off LEAP there, and that might fix that. I also currently running right now is finishing the cutoff of 0.04. So shrinking my radius for localization might improve my results, and that could be interesting for if we do have more variability in the system, which we want, maybe we need smaller correlation lengths for the DA component. And that would be cool if we were able to figure out what that correlation structure should be. But yeah, thanks. That's a positive comment.
Yeah, I guess maybe 2 questions or 1 question, 1 comment. You didn't mention anything about the representativeness there.
Yeah.
And I don't know how specification of that actually will change things. And then I suspect that the vertical localization will actually impact the results as well. But anyway, my question was I'm a bit confused by the freezing point overshoots or undershoots, I guess, whatever you want to call them, simply because, maybe Fred can answer this question. We've been using some of these ENKF reanalysis products, and when we did the comparisons, I don't recall seeing in real applications, not synthetic data sets, but ingestions of observed data sets, raw data sets. I don't recall, maybe these are at time step level. I don't recall seeing this or encountering this issue. That's why I'm a bit puzzled by such large undershoots.
So you were assimilating in real time, real observations?
That's right.
And you didn't see any issues?
Not that I'm aware of. Fred has experience, and Alicia was doing a lot of that stuff too, and I don't recall seeing any, or at least I wasn't aware of anything like that.
Yeah, we never looked for that, but it totally makes sense that you will get this. It's purely like a statistical, so it doesn't care about concentration be positively defined or CIs or whatever. So I'm not surprised that you get that. When we did it was with POP. So what I suspect is happening is that MOM6 is maybe more sensible to that. And so you get more like spurious mixing or something like that. And then that blow the CIs. And maybe just POP was fine with restarting with -3 degrees Celsius and it didn't translate in blowing up the CIs. I suspect that's the only difference, but I will expect to see probably something like that. If you go back and look at our result for this, it just it didn't manifest as blowing up the model in our
It didn't kill, it didn't kill your simulation. It could also be that she was using clamping. I don't remember from the paper, but you can in Dart enforce some clamping. But you have to be careful that you don't want to be non-physical with that too. And we tried that, and we were open to just trying that. And we tried -1.8, and that did run 1 year, and then it died the next for a different simulation. So it kind of felt like we were, adjusting the clamping a little bit to make sure the thing would start again. But now we just follow this linear relationship.
The problem, another potential challenge is that these because you know that there's a limit, lower limit.
Yeah.
but there's also the overshoots on the other side that you are not aware of.
Yeah, I guess I'm not aware of them currently because they also haven't killed the model. I know I'm
Well,
aware
no,
of
I mean,
these
but
because they'll
it's not
kill
going
me.
to result in blow up. If the real
Right.
temperature is going to be like 20 degrees Celsius, and if you are getting 25, the model will be happy to run.
Well, I think we do know that it's still at least realistic though, because we can look at the like sea surface temperature, right? And we haven't seen any crazy increments that would be non-physical in the positive. At least eyeball norm kind of investigation. But yeah, I mean, it's a good point. Like that's the problem with ENKFs in that way is they're not respecting necessarily the bounds that the variables have physically.
Your theoretical freezing curve is based is at surface. You're assuming is at the surface.
I'm doing it all the way down, all
All the-
layers. This is applying to like, because if you only do it at the surface, it didn't fix. Like I'm applying the linear relationship to all layers of the ocean, if that helps. But where this, I mean, I don't know if Ian wants to speak to where the theoretical linear relationship came from, but I can say that the update that I'm applying has to happen at all layers or else SICE will still be unhappy with me.
I'm wondering if there's some kind of pile up of sea ice around Antarctica that like you're then SICE is evaluating. Actually, I don't know if SICE takes pressure when you compute. It does take pressure when you compute the freezing point, right?
I don't know what size those.
Because it might be that water is too deep. I'm just guessing. Like,
Right, like are you saying that you only need to change the surface, like wondering about just the surface layers?
no, like
or-
if there's some pile up of sea ice, and you can see looking at the output, if things are like, especially with the frozen runoff, things can pile up on the sea ice, and then later in the run, the ice is being formed instead of near the surface, like pretty deep.
Yeah, yeah. Oh, yeah. I don't know exactly what's happening with SICE or how SICE is computing that, but I know if you just try to fix, if you think that this problem is just at the top and you just try to fix the first few layers with this linear relationship, SICE will still be unhappy. So,
Yeah.
Maybe we should chat afterwards because that brings up the issue with the fragile ice formation and it should take care of it and the advector errors can cause it at depth, not at this. So anyway, we can chat later.
Right, so let's move to the next.
yeah.
Thank
Yeah,
you
yeah.
one more time. Let's move to the next speaker. Oh, I should have said next speakers. Okay, so the next talk is by Dan, Manish, and Aiden, and they will talk about regional home 6 in CSN via Crocodile and Crocodash. Okay. You have to share it, or if you guys want to speak.
Great, thanks everyone for being here. So yeah, we just decided to collide these three talks into one. I'll note that this time Manish and Aiden coordinated outfits and not me and Manish. So last year, so that's great. Is that on?
Your mic is not on.
Oh, that's great. Okay, I have to repeat my joke.
So it'll talk.
Okay. Thanks everyone for being here. I'm sorry, online people, you missed the joke. So today we're going to, so I'll present an overview of our Crocodile project. Manish will describe some updates on one of our main software products, Crocodash, and Aiden will describe some new efforts in AI. So as many of you know, Crocodile is an NSF cyber infrastructure project that's funded jointly between NSF NCAR and HUI. We are starting our third year on a 5-year project. And this project, so we've got lots of folks working on this at NCAR. I guess Dave is a new addition, still a square peg there. I haven't had a chance to format. But so he's working on some of the SICE connections, and then collaborators at HUI, COSIMA, and Australia, and also lots of help from folks at GFTL. So this project is kind of inspired by the recognition that although CESM, one of our major outputs is global configurations, that regional downscaling is increasingly important for understanding how to communicate changes to human and societal scales. But it's a modeling challenge because you can have a lot of different models that are maybe suited to specific purposes and specific regions. So how can we support this community and also recognize that we have a very finite amount of staff to support lots and lots of models? So the philosophy behind Crocodile is to recognize that a lot of what is needed to build a regional configuration can actually be automated under the hood. So thinking about generation of grids, boundary and initial conditions, even observational data sets. So we think of packaging this automation as like the chassis that we are kind of providing to users, and doing so in an accessible and attractive Jupyter Python interface. And then we also want to give access to ways to modify the model to make it actually useful. So thinking about model parameters, also providing diagnostics, comparisons with observations, including data assimilation, with the idea that with this chassis and these tools that folks can go on and do fabulous things with their regional MOM6 configurations in CESM. So this has kind of come to life over the past couple of years, which has been very exciting. So Manish will describe some of the recent advances on Crocodash. And I just want to give a bit of a feel for what this actually looks like. So if you go to our Crocodile-CESM GitHub repo, there are lots of galleries of notebooks, different kinds of demos you can look at. And so this is a snapshot from one of these demos. So we have individual cells that let you build grids and edit topography. Let's see if I can actually make this play. Advanced threat protection. Okay. That's been deemed an advanced threat. One of the things I wanted to highlight here is, in addition to this kind of text, there's also some really nice GUI features developed by Alpair, also a recent summer intern, so that you can really kind of click and drag your way to the regional domain that you would like to see. So in the remaining time in this project, so we have 3 years, there's a major component of what we're doing is community building. So we have these tools. The metrics for this project is really, can we get people to use this out in the community? So we held the first of 4 workshops in October. So we got a few dozen people from all over here in the Mesa Lab. And it was kind of soup to nuts, starting with Navier-Stokes and going all the way in the last couple of days to some hackathon projects. And I thought it was pretty neat what people were able to come up with in those 2 days. So starting from scratch, we had people modeling biogeochemistry, putting funky topography when the California current wasn't looking the way it was supposed to, even trying things with lakes and sea ice. So that was encouraging and exciting. The next workshop will be held September into October of this year. So we'll be spamming the CESM lists and other places, and feel free to reach out with any questions. And then, we have this kind of development cycle, which takes us from one workshop into another. So in the next, I guess, about 8 months now, our top priorities are going to be continued development of Crocodash. Manish will speak about this next. Development of open boundary conditions within SEISS, and Dave is leading that effort. Cycling data assimilation and observing system design using Dart. So Kate has really kicked the tires on a lot of the MOM6 Dart. And then under the hood, Helen has a lot of new Python tools for using Dart in CESM. We're going to be working on diagnostics. Mike just spoke about that. CESM integration and testing. And then also immediately after this, Enrico Milanese will talk about a near real-time ocean observation database for use for data assimilation and model data comparison. And then longer term, we are looking ahead to a follow-on proposal and hoping to extend these tools to coupled regional Earth system modeling across all CESM components. And so we've had one flavor of this. This is the work that Hung Nguyen participated in this summer on modeling SEIS, regional SEIS. And the last piece that I'll mention and hand it off to Aidan is some work dipping our toes into AI emulation. So here you go, Aidan.
Hi, I'm Aidan. I'm a senior at CU Boulder, and I've had the privilege of working on Crocodash for the past year with Dan and Manish and an amazing larger team that you saw there on the screen. As you can see, though, this crocodile is looking a little hungry, so maybe we want to feed it something. And that's what I've been working on for my senior thesis, is trying to combine Crocodash with this machine learning emulation, like a hot topic right now with Earth system modeling. Why do we want these emulators? First of all, they're super duper efficient, right? When you're running inference or prediction, they're on the order of like 100 times or more efficient than their numerical parents. As a result, they're also really, really accessible. So we use some pretty fancy GPUs here, but a lot of these models can actually even run on your laptops at home. So like easy to distribute, easy to get into the hands of people who want to do science. And they're really modular. So machine learning emulators are agnostic to a lot of the traditional challenges of numerical models, which comes with its own huge set of caveats. And sometimes they imagine that, parts of land don't exist. But it does mean that you can avoid some of these roadblocks that numerical models face and explore and pick apart the models, really grabbing some of these cool features and behaviors that you can't normally. And I want to shout out another package. This is NCAR Miles Credit, which is also, Miles is the AI group here at NCAR. Credit is this Python package for setting up these Earth system emulators. It's really, really powerful. And these 4 people on the right, including the rest of the development team, have just made this entire project possible. I think Crocodash plus Credit have jump-started this in a pretty cool way. So what is emulation, right? This looks pretty similar to a numerical model, right? You have these inputs, then you just step forward in time, and then you feed it back in and you can run your inference forward. But machine learning doesn't have any sense of the physics, right? It's all in the matrices. And so you need this extra little bit in the bottom left, this training data. And this is where a huge roadblock often comes up, is you just need tons and tons of high quality model data so that the emulator can learn what you want it to do. And that's where Crocodash comes in. So for my thesis, I've recreated Carib 12, which is this 1/12 degree model of the Caribbean Sea that was originally done by Giovanni Sejo Ellis before Crocodash existed. And Crocodash has just completely given it these super powered jet boosters. And it has the added advantage of being reproducible and shareable, which Manish will talk about more later, meaning that now this emulator, once it's finished, can be shared and people can generate their own data for inference. And it just becomes this really modular, accessible piece of introduction to regional ocean modeling. And then I wanted to shout out this project that is kind of looking forward. So there's a CSSI proposal that's currently pending that would work to combine Crocodash, Credit, and DART and some of this ocean or observation system simulation that Dan talked about to really have robust emulators that let you explore different features of the system. We're really excited about some of the tools that machine learning gives us to pick apart the behavior of the system that is different from numerical modeling. And a thank you to my thesis committee, which are the names up here. This would not be possible without them. And hopefully I can look like this crocodile friend at the end of May. So yeah, thank you. This was just a brief promo, and Manish has got to take it away. So please come find me afterwards if you wanna hear more.
Okay. Hi everyone. I'm gonna wrap up this talk talking about Crocodash. And Crocodash, as Dan has mentioned, is Crocodile's software setup tool for regional ocean modeling. So what we're going to do in these last couple minutes here is give you a brief background and then the features that are coming out as part of our push towards version 1. And what we're trying to get out of this last section is first, we want your interest in setting up regional ocean models with Crocodash. And then 2, get your feedback as these amazing scientists in the field. Give us some feedback on what we're doing and how we can make it better for you. So as Dan mentioned, Crocodash is a Python package. and it works as in a kind of workflow method. So there's 3 steps to setting up a regional model that we've decided to work in. One is grid generation, so generating all of your grids, and then interacting with your model. So in our case, that's CSM3 and MOM6. And then finally working on your forcing configuration. So that's things like initial and boundary conditions. And Crocadash does this by working in like about 6 API calls that do a lot of power and functionality behind them. And we're on our way to version 1. We've got some cool features we want to show you, and we want to get some advice on where we're going with this and if we can do things differently and make it easier for everyone. So I hope you like the AI generated photos. So one of the first themes that have come out of Crocadash version 1 is flexibility. So as we all know, CSM is amazing at user interaction and being flexible. The idea that you have a source mods folder where you can add in random fortran, it's absolutely insane. Crocadash tries to keep that idea of flexibility so that we can be as moldable as possible to what you want. And that comes up in a few different ways that I think we'll advertise. And one of those is adding a new data set. In Crocadash, we generally use Glory's reanalysis and CSM2 Marble results. But if you want to add your own data set, we have this object-oriented, very verifiable format for adding data. So if you want to use like CSM Large Ensemble, for example, we'll force you to give us all the parameters and make sure it'll work and plug into the Crocadash workflow. Another really quick example is you can add different forcing configurations. Like if you want a different kind of runoff mapping or some kind of different thing, you can actually add that into the Crocadash workflow. And then finally, just this is probably the most boring one, but on the bottom here, I've just put in a command line option. All of the heavy computation in Crocadash can be done offline. So you can set up your regional ocean model with Crocadash on your login node, and then you can submit it to your PBS and Slurm jobs, which I think is just part of this idea that we want Crocadash to dance with you. So it'll be very flexible to what you might need. So hopefully that garnered some interest. Another theme that's come out of this is robust testing. So Dan briefly mentioned this, but we now are adding regional ocean model tests into the official CSM release. So every alpha and beta tag that comes out will run regional ocean model testing that's generated with files from Crocadash. I think that's really important because we can trust what we're doing a little bit more if we know that's being tested in the official CSM release. And then a second part of this, if any of you have met Albert, you may know he's slightly interested in software correctness. So one of the themes of what we're trying to do is really focus on software correctness. More than looking at new features, we want to make sure what comes out of version 1 when it's released is right. Like the data that comes in like Glory's and like CSM data comes out the other side and you're not just getting like a fill value of 0 in the temperature, which will actually run if you do it right. So just keep in mind, we're trying to make sure that the robust testing is happening. I know it's very complicated in Earth system modeling setup. Okay, I'm going to skip this part for now because we're running a bit out of time. This is the whole interactivity grid edits part. And then go to our last section. So that's going to be shareable configurations. And this is probably the most jarring or out of the box thing we're thinking about doing. But it's this idea that you can take your CSM case and pull out all these unique parameters and files and hand them to someone else, like these cute crocodiles kind of show you. And what we're trying to say here, and we think this is a good idea, is this possible? Can we share these configurations so that you can do lots of different things with it? And what we wanted to know from you guys is, first off, is this useful? And then 2, is there anything we can do to make this better for you? So I know that's kind of a hard question. So we've dropped a few use cases and I'll kind of go over them really quick. One of the things you might want to do is fork your regional MOM6 case. Say, for example, you want to add a slightly different COM set, like a new runoff product, or you want to change, like add tides or chlorophyll to your thing. That can be done very easily through this configuration idea. You can output an easy summary of your non-standard changes. So again, that's the idea of pulling out the unique things that make your regional model, and you can see it all. Another interesting one is easily transfer relevant data and configurations to other users, which is the shareable idea. And then 4th, this one is probably my most favorite. It's uploading exact parameters needed to recreate your regional case. So if any of you have read regional ocean modeling papers, in some journals, you actually do need to publish all of your configuration files and stuff like that. And as me and a couple others have figured out, it's like, realistically, we're not going to be downloading that and running it because it's so finicky and hard to use. So one of the use cases for shareable configurations could be an easier way to do that so that people are more likely, or it's more accessible to try rerunning your regional model, which we think is an interesting use case. And then finally, maybe read clean summaries of your case. So you can pull out all the unique information and read what's going on. And so I'll I kind of sped through that, but I'll leave it there as just say, Crocodile version 1 is coming out in April and May, and we have a lot of interesting features coming out in it. We have a little bit of room to run. So we're curious, what might you guys want from version 1 based on what you've seen and what anything else you might want? And then kind of, again, with the shareable configuration idea, how can we change it for you? And I have some really interesting examples that I'd love to talk about, but I'll leave it there for now. So thank you.
You have time for one more question. But remember that there will be a discussion time from 11:45 to 12 in one of the topics is regional one. So one quick question.
I just had a really basic question, Matty. In terms of the input data, with new users, is it easy for them to get the input data either from downloading it from somewhere or from some source, as say if they're not working in NCAR?
Yeah, so input data is it's one of the hardest parts of the process. Yeah, so CSM input data is publicly available. So we have our own data sets we're producing, they're on there, and then we provide APIs to the other public data we have. So you should be able to do everything. There's documentation for things you can, and there's Python APIs you write to download them. And of course, there's stuff that you can't share, it's like protected and stuff like that. But there's documentation that we try to point to. I think yes is the answer to that. Yeah.
Well, let's take the speakers one more time. Enrico, are you there? Can you please share yours?
All right. Can you see my screen?
Yes, we can. Yeah. So our next speaker is Enrico Milanese, and he'll talk about model data comparison tools using Dart and Crocodile. Please take it away.
Great, thank you. So I'm a data scientist and a programmer at Hui, and I'm part of the Crocodile project that Dan just introduced. And I will speak about this model data comparison. And so let's start from the situation where you just ran some ocean model simulation, say MOM6, and you have an output like the one on the left here. You have, for example, sea surface temperature. But you want to know if your data is correct, if your model can reproduce reality. And so, for example, you want to compare the data with recordings from Argo floats. But ideally, you would like more data sets, so you might start to get interested into GlodeUp, spray gliders, the oleander line that is also in this area, and possibly also animal-borne measurements. And so usually the next step then is to gather this data. And for example, let's assume that you're interested in Argo, GlodeUp, and spray gliders. We start with Argo, and so we define the region, the time coverage that we're interested in, the variables, and we fetch the data. Say that you're using Python, we use ArgoPy, which is a package that allows us to do that, and we load the data. We do the same with GlodeUp then, for which we go pick the master file, which is a CSV file, while Argo is in NetCDF, for example, and we load the data. And then same for the spray gliders. And then finally, we merge them in some kind of structure or in some kind of uniform structure that can be a table, can be an array. And we match names. We possibly perform a quality control on the data too. And so we see that there are a few aspects of this workflow that makes it more complex. For example, just by looking at the Argo data is stored in files per float. So we need to process one file per float usually. CSV is an inefficient format compared to other formats. And when we want to make this data uniform, these are the actual name of the temperature values in these three data sets. So we do need to do some homogenization of the data. There are then a couple of bottlenecks due to this lack of uniform access. One is knowledge related, in that, for example, the user needs to learn about how to deal with different file formats and different data structures. and also technological in terms of that some data can have a slow read performance and the workflow becomes long just to gather the data. We haven't done any comparison yet. So within Crocodile, one of our goals is to make life easier with this regard. And so I'm introducing CrocoLake here, which is a cloud-optimized collection of observations. I would say it's Crocodile's best and freshest collection. It's maintained by me within the Crocodile project. It currently has roughly 1.2 billion observations, both physical and biogeochemical. As I mentioned, it's a collection and currently has Argo data, which of course makes up most of the observations in numbers. Cloud-up spray gliders, the oleander temperature measured through the XBT sensor, and OCS sail drones data. It only contains data that are already quality controlled by the provider. It contains instrument errors when provided, but no representation errors. It's updated weekly because the Argo data is updated frequently, and also the oleander data is updated not as frequently as Argo, but multiple times throughout the year. And it comes by default in Parquet format, but we can generate it into DARTS format, which I touch upon later. I want to stress the best and precious aspect, as in best because we only keep quality control data, and freshest because we update it weekly. Another benefit of CrocoLake is that because of the collaboration with Susan Whitefeld and David Nicholson at WHOI, we are also in close collaboration with Argo-related projects and with the Oceans Vital Signs Network, which is a WHOI project aimed at studying the carbon cycle in the Northwest Atlantic. So we have a special interest for the Northwest Atlantic when it comes to including data sets in CrocoLake, but we're not limited to those. Finally, want to stress that CrocoLake, as I mentioned, comes in Parquet format, which makes it language agnostic. You ideally can read it with any coding language, and we provide examples for how to access it in Python, MATLAB, and Julia. So this is actually a video of the data that is available. Actually, that was available up in July 2025. And so you will see it starts from 76, and now the time is going forward. And you see that all this data is mostly glowed-up lines. And then at some point, we will see the Argo data starts to populate them up. I guess I can skip a bit closer to the 2000s. Okay, and here we see the first floats. And let's skip a bit farther. I find it also very interesting to see the impact that Argo data has on the community. And here in lighter blue, you see the Spray Gliders project. Then at some point, the sail drones, here they appear on the Pacific. And this was made before I included oleander data, but otherwise we would see also a line of oleander data between New Jersey and the Bermuda. So this is how it looks like now to load the data that I showed in the pseudocode in the early slides. And so with just basically 4 lines of code, we can define what variables we're interested in. We define the regions and the time that we're interested in. And then all the data is loaded into one table. And so, for example, we can see that different databases have the same data structure. The data is harmonized. And the syntax is very similar also for the MATLAB and Julia examples. So this is the plot of the data just like loaded with the cell that I just showed the previous slide. So this is 10 years of data in this region of the Northwest Atlantic. And this is how it is shared across the different data sets that are in CrocoLake. You can see the spray gliders, the oleander line that I mentioned, the vast number of Argo measurements, and the glowed-up bottle measurements. Yes, and we can see clearly how like the spray gliders cross the Gulf Stream, also the oleander, for example, and so on. A couple of words to compare CrocoLake with the World Ocean Database, which I believe is the one that most people are familiar with. So of course, WOD has long been established. They perform extra and ad hoc quality control, and is probably the largest records of observations in ocean sciences. At the same time, I like to say, to put this here as in if you as it is in a beta version, this Croco Lake, I invite people to give me feedback on what direction we can take it to. And also Croco Lake is fast and cloud optimized because of the Parquet format. World Ocean Database is also updated, I believe, every 5 years for major updates, while Croco Lake is updated more frequently. The next step, the next thing I want to touch upon is the comparison between model and observation. So the idea is that we have a tool now, well, it's not an idea, we have a tool now that allows us to go from the model data that we have here on the right and the observation that we have on the top right. And then with a few lines of codes, we can map the model data into the observation space. I'm sorry, I think my slides have issues. Or is it my, oh no, it's my mouse ran out of battery, I believe. Sorry about this. Okay. Yes, perfect. Okay, and so to do this, to go from the model data to interpolate it on the observation space and define this widget that allows us to study it, we use Dart under the hood. So Dart was mentioned earlier, is this data simulation software developed and maintained at NCAR. And in particular, we use the Perfect Model Ops script for those interested to interpolate the data. We do this with a code that is called CrocoCamp. For now, it will be renamed. So the user doesn't need to use Dart directly, but they just run these few lines of code, again, in the idea of having these Python notebooks that are easy to use. And then Dart will be run under the hood by the code. Okay, so for the one detail about the observation is that whether you use Croco Lake or WOD, they need to be in Dart's format. So for Croco Lake, Dart needs observations to be in an observation sequence format. And for Croco Lake, there is a so-called converter that allows you to, again, select the region that you're interested in and generate these files specifically. I want to give an example of the workflow of how this works. Let's say that, for example, you have a model output. For the sake of the example, I'm taking one file with 10 days of simulations and daily averages. And then we have 10 files of observation sequence files containing observations from Croco Lake. Then CrocoCamp splits the model output along the time dimension, matches each day of the model output with the daily file of Croco Lake, and it interpolates the model based on this pairing, and it never reuses the same observation file twice. This comes with the caveat that then the resolution of your comparison is based on the averages that you stored in MOM6, for example, and also that the observation sequence files must be generated in that resolution. This is the same, but visualized differently, that maybe one of the two forms is more digestible for someone. And so we have one output file from the model with daily averages, several observation sequence file. What CrocoCamp does is splits the output file into multiple temporary files, and then generates the pairing and computes the differences between interpolates the model data onto the observation space, and computes some differences and some statistics between the two and stores it in a Parquet file. Recap of the ingredients: you need a model output, which can be MOM6 or ROMs. We also support ROMs. You need an installation of Dart, CrocoCamp, and observations in a sequence format. If you don't want to use Croco Lake, Dart comes with several converters, so you might find a converter that already exists for the dataset that you are interested in. And this is my final slide. So some outlook on these projects. So one of the plans is to make the interpolation windows more customizable, what I touched upon in terms of resolution. Also, we got news last week, I believe, that an internal project at UCAR was selected for funding. So later in the year, I believe in December, we will probably organize some activity to import further ocean observations into Croco Lake. I'm also working on a template repository, again, linked to what Manish and Aidan and Dan were talking about earlier, like a template repository that includes the tools that you showed in the previous talk and the tools that I presented here as a use case so that other users can use them as a starting point for their own regional studies. And we will rename CrocoCamp, as I mentioned. And also I'm working on improving the efficiency of the code for much larger simulations. And that's it.
Thank you, Enrico. I have time for questions now. We can actually open for the discussion as well, but if anybody has a particular question for Enrico.
Thank you. That was really very impressive. I was wondering why your collection of observations does not include the buoy array along the equator, but over the Indian Ocean, the Pacific, and the Atlantic. There are many buoys that I think belong to NOAA. And I was just wondering, maybe they don't pass your test for quality control or something.
No, long story short, I have not had the time yet. As Dan mentioned, the Crocodile project just started its third year, and like this is what we've had the time to add to. There are tools that like the tools to generate Croco Lake is open source, so people can also add to it. And yeah, it's on the pipeline it's on the list of many data sets that I would like to include, definitely. And thank you for showing interest in it.
Thanks.
I have a question for you, Enrico. So World Ocean Atlas provides the gridded data. There's like a mean product, and there's also means over certain decades. Would you be able to do the same thing with Croco Lake? Like, can you generate a gridded product and then do like over specified years?
So yes, that's actually something we are planning the medium term here at WE of generating a gridded product out of Croco Lake. I don't know the details of that yet, so I'm not sure how it would, and I'm not that familiar with the World Ocean Atlas, so I'm not sure how it would compare. But the idea would be, for example, to have a standard levels, either in depth or density space for it. And yeah.
Cool, thanks. All right, let's thank you, Enrico, one more time.
We have 12-ish minutes to talk about next steps beyond CSM3 from the ocean model sketches. I'm going to share my screen. And this is what we had in the agenda initially, but it can be anything else besides the screen. So, okay, we have time to share your thoughts on what would you like to see, what's working, what's not working, ideas for experiments. Who wants to talk? Dan, please.
I was wondering if you could just give the lay of the land on high-res ocean and couple, just like what general timelines look like and goals.
Yeah. So 2036 will be the year where we will start investing in the high-res CSM3. We have done some prototypes of forced case with CSM and Global 112 NGRA forcing. It was about like 25 years. We had 2 long runs, one with a hybrid coordinate, one with a C-star. There were issues with the topography that we were using. I used an old file that Crank generated, In the meantime, we have gathered, I think, a couple of times over the couple of months to talk about next steps. The very first next step is to update the topography, and Frank has done that already. And he used actually a state-of-the-art tool from Alan Walcroft to generate the topography. And it has topography and CMAS. And there was a meeting, I think, a week or so ago where people talked about the set of parameterizations that first of physics that we want to use for the high res. And yeah, we are now at the stage of time permitting, recreating the files needed within CSN. And then we got the green light from Dave Lawrence to use about 7 million core hours to do a run with the forced Ocean CIS Global 112. I don't know if anybody else wants to add, Gokhan.
Yeah, I mean, that's just to add, I mean, that's the plan. We are also getting help from Mehmet from Istanbul Technical University. And we actually, that meeting, we postponed it because you were not available for the parameter setting. So I need to set that thing up still. I haven't done that. And then the goal is then, as John talked about this morning about the Turbo project, so eventually combine what the outcomes of Turbo is to expedite the GPU enablement of that whole configuration. And not only Turbo, but also another like SHORE project. That's what we have at the National Academy of Sciences, sea level change project. Quite a few projects rely on this now, especially with the success of the Mesa Clip project. And we are eventually, the other project that is out there is the Storm Speed. That's creating the non-hydrostatic dynamical core with the spectral element dynamical core for CAM. So the goal is essentially to combine all of those together to create the next generation of the CSM high-res. And then there are additional efforts that will be, I'm trying to be politically correct here, that will be sort of pursuing higher resolution versions of MOM6 up to maybe 1/36 of a degree, coupled to either global or regional versions of MPAS for short timescale integrations, whose Ben Barr is our new hire. He'll be starting on Monday officially, so he's still a guest here today. Monday he'll be the
last day of my postdoc.
Last day of your postdoc, so he'll be actually working on that as well. So.
Okay, any other topics? The one thing we'll be doing this year, normally every time there's a new allocation, we have to provide a justification of the previous usage of the computer, but because of the finishing of CSM3, everybody's overwhelmed. They kind of waived the need to justify, and also they were like less. They usually would come up with a proposal for the next 2 years. And my understanding is that we won't need to do that unless we want to. Which is nice, but also like if there's special needs, and I think all these high-res configurations are kind of a special need. We might want to contribute even though we were not asked to provide some justification, and you may ask for more time on it. Justin?
Another item not mentioned there, that a small group of people, or actually kind of medium, big group of people, looking into the SE flux scheme and updating it, and working with Elizabeth Thompson at NOAA, which kind of gives you a hint that core, the NOAA SE flux scheme is being pursued as the next SE flux scheme in CSM3. But the status at the moment is there's options of 3 SE flux schemes in CSM, Largen, Jaeger, Thor, and University of Arizona. But we're pursuing the core or Farrell et al. Or NOAA scheme? Because it's being actively developed, but the other two are not.
Yeah, and Dave Lawrence mentioned yesterday, there were, I think, a couple runs done when we switched to core, but things got completely out of balance. A lot of diagnostics were not good. So it seems like this is a multi-working group effort that we need to, and also we should try doing a GCase with that as well to see how that looks like.
Yeah, there was a meeting, and I think when you were on parental leave, so maybe you should be involved in the next one, and there will be another one in maybe a couple of weeks' time.
Sure. Well, yeah.
Just to clarify though, it is not CSM, the released version that we are targeting in June. So any change in bulk fluxes will come later. So yeah, just to be clear. Yeah.
Yeah, and yesterday we saw from we see her name now from Leno, the dog from Leno, Aaron. They were able to notify late larger Jaeger by adding that extra term that accounted for the waves, which that seems like a low-hanging fruit for us. Like we could try something like that just since we already have all the ingredients needed. Okay, any other topics?
I guess, Gustavo, are we thinking of proposing any big experiments for the allocation?
I think it's a TBD. Like, as I said, we got Dave Lawrence approved about 7 million hours for these.
No, I meant for the next cycle. That
one we're not asked to provide a formal proposal, but given that we have all these high res in mind, we might want to. Moment?
Yeah, it's like question. What do you plan to store for these high-res outputs? Because I think if you want to compare to other high-res models, it would be good to have some, not long, but some areas with actually daily output or whatever, right? So something that you actually can see how the currents behave. So that would be a bit more that you would normally do with the simulated run.
Yeah, so 3-dimensional daily output.
Not just the surface. People just listen.
Yeah, we will have surface daily output. This is easy. Yeah. The problem is 3D.
Are these historical runs?
The high rise that we're talking about that we've done and we'll do next is they're all forced GRA case. So yeah, it's not a couple.
But just to be clear, so Fred will be talking about the existing high-res effort. So we can essentially take that thing as a sort of template and then go from there. And the idea is essentially, just to be, our existing high-res effort is based on CSM 1.3, which is 20, well, not quite 20. It's almost 10 plus years old. And in CSM2, we on purpose skipped high-res because we didn't have the computer resources, we didn't have the people resources. And the goal was to recreate an equivalent version in CSM3. And ideally, once, as Gustavo indicated, we spent some time this year to create, it's not easy to create the high-res version with the balancing and all that stuff. And we can hopefully repeat what has been done with the existing 1.3 base.
If you're lucky as a GFGL with Griffey's, zero rest time.
Sure. What I was thinking is they have plans to output data on the moorings point that Jacqueline mentioned, because these are pretty useful diagnostics.
Yeah, we haven't talked about this, and the MOM6 has the advantage of you can specify
points,
sections, and give you a point. So yeah, I think that it could be a useful thing to have, for this particular case. Although, if it's at the surface, then we'll have high frequency daily. But if you want unidirectional, then one way might be going to these predefined sections, which we haven't specified for the high res yet, for the low res. Dan?
So Sizzle sent out a request for input on what the next machine will look like. I mean, have you all crunched the numbers and what does it take to run the next Mesa Clip and CESM3 on 6?
I mean, the next, well, John may say more about this. Do you want to say more about that?
No.
Sure. I mean, one goal is essentially that's what we are trying to target with high resolution. Texas A&M is going to have a big GPU system. So that's the idea, one at least.
We need the whole of CESM on GPUs to do that.
Yeah. Maybe.
Okay.
Okay, so it's 12 o'clock. We can end the discussion and go to lunch, and we'll be back at 1:30 for the final session.
All right, thanks everyone for sticking around for the final session. We're doing high-res CESM today with Mesa Clips, starting out with Fred, and then we got Ben Lombardi and Justin after that. I think we all know how this goes. So without further ado, Fred, go ahead.
Thanks, Ian. Is the mic okay? Okay. So CSM high-res. So a lot of the high-res stuff that we have done in recent past was done under the umbrella of an NSF-founded project called Mesa Clip. And so I'm just want to give you like a little bit of an overview of what is available, what we have done, and just some highlight on like what you get essentially by going from the standard like 1 degree model to high-res. By the way, high-res is like 1/10 ocean and 1/4 degree atmosphere, because that high-res can mean a lot of things to different communities. So this is high-res for climate, so it's not like K-scale. One of the things that we have done recently is get a logo. So this is the logo for the project. So that's one of the accomplishments. And I even have some stickers. So if you want, I can give you some later at the end of the talk. So during the past like 5-6 years now, even more than that, we have like used this like CSM 1.3 configuration, as I say, with a 1/10 ocean, 1/4 degree atmosphere. And we have been able to like build like a very unprecedented data set at this kind of resolution. So I've listed like I think all the simulation we have done, but I may be missing a few. All the simulation in green are publicly available on the GDEX or RDA, previously called RDA, a Research Data Archive, to the community. And so we have like a 500-year PI control. I've done like 80-year 1% CO2, 4x CO2. So it's like instantaneous quadruple of the CO2. More recently, and this is ongoing actually, that's why those are not like in green. I've done in a 500-year plus like oozing experiments. We'll talk a little bit more about it later. And then we have like a pen ensemble member of like historical RCP 85 at RCP 60. We have one ensemble member for RCP 45 and 26. And as Gorkan like alluded, we have a new NAS project, National American of Science. And as part of this funded effort, we are going to extend the RCP 45 and 26 to 10 members each. We also did like a ozone withholding experiment. I will talk a bit more about it later. And then we have kind of like the AMIP style simulation, all the high-res MIP simulation. And one of the big like effort that we're currently working on is like the HRDP, so high resolution decadal prediction. So it's going to, once completed, we will have like 10 ensemble member, 5 year out, initialize twice a year, every year from 1980 to 2023. So that alone is going to be, I forgot, I did the math, it's like 2000 years of high res and like 2 or 3 petabytes of data. So So that's what we have. If you are interested to work with this data, as I said, there are like most of them are at this point are publicly available, and we have a project website hosted on the CGD server, and it's like a good place to start. Like you have some information, you have like all the link or way to access the data on GDEX. I try to keep it up to date and add like if people like use the data and publish analysis, I usually try to keep like a bibliography up to date so like people can easily see what have been done and educate themselves about the data set. GDEX is a very powerful like tool, so you can download the data to your home institution if you want to. Everything is time series, so even if the ensemble of the data set is like several petabytes, you can just download the variable you want. So if you just want to look at SST, you can get only SST. So it's a lot more manageable. But it's also give you access. So the data is hosted on Campaign storage. That means that you can if you can get an allocation to work on our system with Casper, you can work directly on the data on the NCAR side, which is the easiest thing to do. And there is a way to get allocation for student postdoc, especially people that are hosted like in a US institution. It's pretty easy to get like a pretty decent amount of time to work on the data. So I encourage you to look at the opportunities for that. So just a few highlights on the what you gain essentially from moving to high res. So this is like just looking at extreme precipitation. So you have the observation on the left at the top panel, the high res simulation 10-member ensemble in the middle, and the low res equivalent on the far right. And so, I mean, quickly, you can see right away that essentially the high res look like the observation, where the low res has a lot of biases and deficiencies. And this is like the high res MIP, so it's usually like about the same class of model. And you can see that it's not just our model, essentially, like usually moving up to this resolution, like you get this kind of like improvement. And again, like as a pendant to the 10-member low res, you can see that CMEP6 is producing results that are consistent with our low res also. Yeah, just a quick like so it's not just like extreme precipitation. I mean, you can see from this PDF that actually any precipitation above like maybe 40 millimeter per day, the high res start to really significantly do better than the low res. So it's not just extreme; it's more like intense precipitation in general that are vastly improved. And over like nice animation that we did. Well, actually, Dan Fu did. It's one of the lead of the project. So now we're looking at grayscale is like the cloud, precip are in the color, and then we use like a tracking algorithm called MOAP to. In that case, we are tracking like what the mesoscale convective system MCS is, and so you can see that a lot of like the intense extreme precip are colocalized with MCSs. So it's like make nice picture, but we can go a little bit further. And so here what we did is more abstract like MCSs, but also a large variety of like dynamical like feature like front gravital tropical cyclone and atmospheric river and etc. And so what we did is we tracked all those features with MOAP. And then we looked at extreme precipitation and tried to essentially correlate like what are the drivers for the extreme precipitation. So when we identify like extreme, we look around it and identify what is the feature that what of those like MCSs, AR, etc. Is happening at the same time. And so what, again, you can see is like observation, high res, low res. And observation is actually ERA 5, so it's take it with a grain of salt when I say observation. But what you can see is that the high res essentially agree pretty well with like ERA 5, and MCSs are one of the features that often like drive extreme precipitation, where in the low res we have a completely different picture, where everything is like jet and font, and so we think that like we get this very good like matrix that I show in the previous slide for the good reason, essentially, because the underlying dynamic is appear to be right in the high res and like vastly improved compared to the low res. We have also looked at TCs, so that's another place where the model shine compared to the low res. So again, like observation, high res, low res. So I mean, we still like, I mean, it's not perfect, but it's vastly improved compared to the low res, and we now start to have like Cat 5, at least Cat 4, maybe a few Cat 5. We're still, a little bit, and it's not surprising because it's a quarter degree model, so 25 kilometer, we don't expect essentially to have enough resolution, but to fully resolve like TC, we think of the model as TC permitting, but it's not resolving. One thing, so no, we think that the model essentially do a much better job and capture this much better than the low res. So we can look at projection with a little bit more confidence. And what the model show is that in terms of occurrence, which sounds maybe counterintuitive, like for example, there is a decrease in occurrence in many regions. That's can be seen like with all this blue area, and they are statistically significant. Despite the decrease in occurrence, if you look at trend in annual precipitation induced by TC, at least all the US East Coast is going to see an increase by the end of the 21st century. So there is less tropical cyclone, but they are more intense. They have more rain associated with them, so they are going to be more damaging and more forceful and have more like societal impact. So we need to be careful. Like it's not because they are going down that it's necessarily better. Another thing that we maybe were not necessarily expected as much as like improving extreme is we are seeing like very nice improvement in long-term trend in SST, and especially like in the South Pacific. So this is low res, high res, and the observation. And you can see this blob of like cooling is even in the ensemble mean, it's showing up pretty nicely in the high res, and also the cooling in the tropic, which is completely absent in the low res. And again, this is not like a feature of our model. If you look at CMAP 5, CMAP 6, they all show something that is very consistent with the low res picture here. If you look at individual member, no, we have some member, including this one, member 10, that really start to look like the observation. And so that was pretty, I mean, that's something we were not necessarily expecting. And we're going to we're looking at it more in detail. So we have a student like at Texas A&M, previous POCHCO, that have a paper that just got submitted looking at, starting to look at this. But bottom line is like we think that it's a combination of like ozone forcing and ocean dynamic that is better, and so we have like better like heat transport in the high res, especially from the AD, that let essentially the cooling manifest in the high res and mute it in the low res. As I say, we have done like 4x CO2 experiments. So one of the goals here was to look at does resolution impact climate sensitivity. One of the metrics that we use often is, again, like those 4x CO2 experiment, and then you do this linear relationship between the radiative imbalance and the surface temperature, and then you extrapolate to essentially the model being equilibrated, so you have zero imbalance. So that gives you like this 6 point something, and then it's quadruple CO2, those you divide by two, assuming a linear relationship, and that gives you this the equilibrium climate sensitivity that we use to quantify essentially how sensible the model is. By this metric, like the high res, low res, they look like pretty much the same, which is always not surprising depending on who you talk to. It was surprising to me. But if you look at regional, if you look at it regionally, then there is a very different picture that starts to emerge. So now this is just like the warming during the 4x CO2 for the high res, low res, and then this is the zonally average for each model, each resolution on the right side, and you can see that the high res is producing a lot more warming at high latitude, and on this, and you have this kind of like south hemispheric response where essentially all the north hemisphere is getting warmer. Compared to the in the high res compared to the low res, and in the south hemisphere it's the opposite side. Oops, wrong way. And what we are finding out is that it's actually due to mostly a response to AMOC that is not collapsing. So AMOC at 45 here time series during the it's only 80 years what I did. So, I mean, it should go all the way to 150. I'm not sure I put the wrong panel here, but you can see that essentially AMOC is not collapsing in the high res and even like recover during the second part of the simulation where it collapsed in the low res and stay collapsed all the way through the end of the 150 years. And that had like very strong implication for like the meridional heat transport. So now the solid line are showing the heat transport, northward heat transport in the model. So same color panel, like high res is red, low res is blue. And this is for the PI, during the PI control, essentially. And then like the dotted line, so the change in heat transport at the end of the 4x CO2. And what you see is that because AMOC is collapsed in the low res, so you have a big drop, like almost like 80% of the heat transport essentially is gone, where in the high res, the heat transport is essentially the same than during the PI control. So we are able to bring like a lot of heat northward essentially because we still have like an healthy meridional overturning circulation in the high res and not in the low res. This like AMOC sensitivity is actually found in over simulation. So now we are looking at relationship between AMOC strength and global level of warming, and so it's just like essentially I bin like the level of warming in the model, and like and create like a PDF for each bin, and this is like the 99 percentile, the 66 percentile, and etc. And the solid line. The thick solid line is the median. And so you can see that the relationship, there is about 50% a stronger decrease in AMOC in the low res for the same level of warming, essentially, of surface warming. So that appeared to be like something that started to emerge, that in the high res, essentially, AMOC is a lot more stable or resilient than in the low res. Another set of experiment that we recently started is the Hoosing experiment. So again, like the goal was to assess like AMOC stability and threshold, like in respect to Greenland ice sheet, and try to answer the question: does like explicitly resolving 80s in the model essentially change those threshold? So we're using this like experimental setup. So the plan is to, well, we are well into it now, but we have run like a 200-year simulation where we ramp the oozing at a rate of 0.25 spherical per century from the PI control. And then we stop the forcing at year 200 and we keep running essentially without forcing to see how AMOC will recover. And the oozing is applied only like around Greenland, and it's also applied at depth. So I forgot 50 meters. So we have a vertical, like e-folding time scale over 50 meters. So it's not just surface, which is a lot of time those oozing experiments are done just at the surface. And I think that can change the response. And again, like here we are seeing that AMOC is more resilient in the high res. So you can see at the beginning, essentially, AMOC try to not collapse. And then like at some point, when we really start to have like a lot of fresh water, we are able to shut down the deep water formation, I think, in the lab C, so AMOC collapse. But we can also see that near the end, we start to see like sign that AMOC is actually restarting in the high res. So I was like, oh, it's looked like AMOC is going to restart when I get to year 400. So I started to extend that simulation a little bit and know there is clear sign that it's trying to restart. So I'm going to keep that simulation, I think, going, and I'm going to extend the low res, and maybe we can get those like AMOC hysteresis plot that people often looked at in the true resolution. That was the highlight I had for you. I mean, in interest of time, I think I can just like leave my summary here and take question.
Maybe time for one question before we go to the next.
Thank you. This is really interesting. Regarding the tropical cyclones, did you check to see if the proportion of storms that make it to category 2, 3, or 4, if that was consistent with observations, or anything like
Again,
that?
like we don't have like Cat 5, and we know that we are underrepresenting there, but I think it's resolution. Dan Fu at A&M is like the person like really looking actively on cyclones. So I guess it will be good to talk to him about that. I'm not sure if he has done that. Do you know, Gökhan?
But we do not get the stronger storms that round up category number 5. And then if you notice that our latitudinal extent is too much compared to the observations in high-res. So those are the two things that we flagged.
Okay.
But I think you looked at the individual bins, but I don't remember how they compare.
Yeah.
But on those plots, there were actually numbers for each boxed basin area, and they match quite well in terms of numbers with the observations. Interesting. So each inset that
so the number is the occurrence in each of the blocks, and so you can see that the distribution, except for some where like the South Pacific, for example, is one where the high res is not doing good, or but overall, they are much closer to the observation than the lowest.
I think we can do one more with Steve's question.
Steve.
Go ahead, Steve.
He's muted. You're muted, Steve. Okay.
So this is tropical cyclone permitting, right? This is not resolving.
Yeah, it's not resolving on that 25. Steve, you have a question?
Steve, we'll come back to it. We're already a little bit over, so I think we'll just bring Ben up.
Yeah, but
So leave the sticker here if you want. Help yourself.
All right, next talk by Ben Lombardi, and it's playing automatically.
Okay. I'm going to talk to you about some work I've been doing with Dr. Grooms and Dr. Kleiber down the road at CU Boulder on characteristics of mesoscale eddies. and eddy permitting ocean models and reanalysis data sets. So I'm sure, as many of you already know, mesoscale eddies are large rotating masses of water, typically around 100 kilometers wide. And it turns out, thankfully, at least for my research, that they're really important to the climate and play a pretty significant role in regulating the exchange of heat and carbon in the atmosphere, as well as the transport of heat, salt, carbon, and other nutrients all around the ocean. And so our motivation kind of for this project has been that climate projections with eddying ocean components have only recently started to become more widely used. And despite their critical role in understanding and forecasting climate characteristics, these eddy permitting models have not been rigorously explored to verify that the resolved eddies are realistic. And so we're kind of aiming to investigate how realistic these resolved eddies are by comparing them to observed eddies in altimetry data. And so I want to talk about 3 different data sets today. Our observations come from the Absolute Dynamic Topography Field, or ADT, from the Sea Level Delayed Time 2024 data set, which is at a 1/4 degree resolution. And then we also look at the ORS5 reanalysis data set, also at a 1/4 degree resolution. And then we were also provided data from a GFDL OM4 model, which was kindly provided to us by Alistair Adcroft. And it should be, I do want to point out that the OM4 model, we do regrid it due to some limitations in the detection algorithm from the 1/4 degree nominal tripolar grid. And so we regrid that to the same 1/4 degree lat long grid that the reanalysis and ADT fields are on. And speaking of the detection algorithm, we use the open source Python package, PyEddyTracker, also abbreviated as PET. At a very, very high level, what this algorithm does is it detects local SSH mins and maxes, and then forms closed contours around these extrema. And if some certain extrema are met regarding minimum amplitude and minimum area, then it's classified as an eddy, and we're going to refer to that kind of classification as a daily eddy detection. And then the way the algorithm associates one daily eddy detection with another to form eddy trajectories is based on the overlap between the effective contours of these daily eddy detections. And so we end up using the same detection and tracking parameters as the Mesoscale Eddy Trajectory Atlas or metadata set, specifically the 3.2 version delayed time. So first off, when comparing these data sets, we're interested in just the total number of eddies, which we're interested in at both the daily eddy detection level as well as the eddy trajectory level. And due to some concerns we have about the resolution of the altimetry maps, both spatially and temporally, we're only going to end up considering eddies that live for at least 6 weeks, as well as that are outside of the kind of middle equatorial band, 15 degrees south to 15 degrees north. And so there's a very big table up there with all the data sets. Just looking at cyclonic eddies, ADT has about 750,000 per year. ORS5 is about 610,000. OM4 has about 565,000. And then you can see kind of a similar trend holding for the number of tracks, with ADT having about 8,100, ORS5 having about 5,900 per year, and OM4 about 5,200. That's a lot of numbers, but generally just ORS5 and OM4 have about 20% fewer daily eddy detections per year and about 30% fewer trajectories, with OM4 being slightly worse in both of those categories. And so we know that both ORS5 and OM4 are missing eddies, and that kind of begs the question of, well, where are they missing eddies? And so to help answer this question, we can look at eddy census, which is just the number of daily eddy detections per 1x1 lat long box, which we are kind of displaying in those first 3 panels. And then that final panel, we're displaying the zonal average of cyclonic eddy census. And it looks like they're mainly missing eddies in kind of the mid latitude, specifically around 30 to 45 degrees. But it does look like they are capturing a lot of the broad spatial patterns, as well as having a similar number of eddies at high latitudes. And so we can quantify their ability to capture this pattern by looking at the anomaly cosine correlation of these maps. And so between ADT and ORS5, it's about 0.62 and 0.53 between ADT and OM4. So they are picking up some broad spatial patterns of eddy census, but it does look like they are missing eddies in most areas of the globe. Another characteristic we're interested in is eddy amplitude, which is defined as the magnitude of the difference between the extremum of the eddy and the surrounding SSH. And I'm going to show like quite a few of these kind of 6-panel figures here, so I'm just going to explain what they are real quick. So these first 3 panels, A, B, and C, are displaying the mean of the eddies in each 3x3 lat long box. Panel D here is a global empirical scaled PDF of the quantity interest. So it's scaled, so the y-axis is representing average eddies per year per units. And then panels, these bottom 2 panels are just showing the difference between ADT and each respective data set, where it's ADT minus the data set. And we're only showing areas that are statistically significant, and we're graying out areas that are not statistically significant, which in this case is given by these little black dots. So in this case, these differences are statistically significant almost everywhere. But just looking globally, global averages, for eddy amplitude, ADT is about 6 centimeters, ORS5 is about just over 4 centimeters, and OM4 is about 3.6 centimeters. And so both ORS5 and OM4 are deficient by a fair bit in amplitude globally. And we can see by looking at the global and scaled PDFs, this is mainly because OM4 and ORS5 have too many small amplitude eddies and not enough large amplitude eddies. That being said, though, looking at these mean maps, they are doing a pretty good job of having a larger amplitude in most of the major current regions. Particularly the ACC, Gulf Stream, and Kuroshio extension, although they are kind of missing this high amplitude eddy region off the coasts of Australia. And we can see this reflected in the relatively high anomaly cosine correlation between all these maps, about 0.79 for ORS5 and 0.67 for OM4. So while they are globally deficient in amplitude, they are, relative to their means, they are capturing the pattern quite well. Another attribute we're interested in is eddy area. And we can see that eddies in ORS5 and OM4 are quite a bit larger than those in ADT. Both reflected in these global means, as well as the maps. And we can see in these different maps, it's blue everywhere, which means that ORS5 and OM4 are larger everywhere. And it's also, these differences are also significant almost everywhere. So they are quite a bit larger. However, similar story to eddy amplitude. The anomaly cosine correlation for these maps is quite good, 0.8 and 0.67 respectively for ORS5 and OM4. And then the last one I'm going to talk about today for the eddy permitting models is eddy lifetime. So generally in ADT globally, eddies live for about 94 days, and ORS5 it's about 105 days, and OM4 it's about 110 days. Looking at the maps, though, they don't do a great job at capturing the kind of spatial distribution of eddy lifetime, which is reflected in these pretty low anomaly cosine correlations. They're especially kind of missing this high eddy lifetime region off this west coast of Australia. And while the reanalysis data sets does kind of represent the Aglohas rings, these are kind of missing from OM4. That being said, though, we did not test that we did not find that many of these differences outside of this region in Australia are statistically significant. That being said, though, we do have substantially fewer samples for eddy lifetime, as it's a trajectory level statistic, while the previous 2 are detection level statistics. So we have, almost 93 times more samples for the previous 2. So we're not able to find that these are statistically significant, mainly because we don't have as many samples. But so concluding thoughts, quarter degree models have substantial room for improvement, even in the reanalysis data sets. And at a high level, eddies are larger, weaker, and live too long. That being said, though, in quite a few cases, it does do a moderate job at capturing the behavior of these characteristics relative to their means. Some future work that I'm going to show a little bit of after this is we're investigating high resolution models, specifically MesaClip. And our kind of goal is once we're done investigating these, we really want to use these high resolution ocean models to affect the effects of climate change on eddy characteristics. And then we're also interested in developing model parameterizations to help models better capture these eddying behavior. And so in the last few minutes, I'm just going to display some results that we have from MesaClip. On the figure on the left is the same quarter degree ADT data. It does look a little bit different than the previous slide for eddy amplitude that I showed, as the color bar is a little different. But comparing ADT and MesaClip, it looks a lot better. We see a pretty substantial improvement in ACC, the anomaly cosine correlation going up to 0.86. And instead of being deficient by like 2 centimeters, we actually have a little bit too much eddy amplitude, with it being about 7 centimeters in MesaClip. And if you compare MesaClip to a higher resolution ADT data set, this difference in means does improve as well. And then another result I have is for eddy area. Eddies are still a bit too large, but we do see the size in the high-res data come down quite a bit, as well as an improvement in the anomaly cosine correlation as well. But we do see that in both for eddy area and lifetime, that the differences are still significant as well. Yeah, and that's all I have, and I have some time for questions.
Right.
So is this ADT product out of Nadia Altimeter?
Yeah, it's derived from altimetry data.
Okay, right. So they have kind of complicated gap filling algorithms when they do those.
Yes.
Right. And then in particular for your high res comparison, do you kind of reproduce the basically smooth quite a bit?
So we've spent a lot of time thinking about what it means, like compare apples to apples with these data sets. And I didn't present the results for this, but we're thinking moving forward that if you interpolate the quarter degree ADT data to a 1/10 of a degree, the same 1/10 of a degree grid, that is a fairer comparison. And it does, the MesaClip ends up being closer to that field than it does the quarter degree as well.
I'll also comment that those regridding the regridding algorithm, or the algorithm, not regridding, but to go from the along track to this SSH product is not publicly available. So we can't play with that to see what happens.
So this is some optimal interpolation involved. Okay.
Right, Justin and
Just a very quick question, Ben. MesaClip, was that a coupled ocean atmosphere run or just the ocean run?
I think it's good coupled. Yeah. And this is from, and specifically we used 1993 in MesaClip to 2005, while the ADT data goes from 1993 to the end of 2023.
Yeah, so you had a comment up there about improving quarter degree simulations. So what can you do other than improving the resolution?
When we started this project, I think we had some more hope for improving quarter degree models. We haven't looked to see what effect backscatter has in them. So that is one possible scenario, but we have looked into a lot of categories besides the kind of 3 or 4 characteristics that I presented, and the difference is quite large, that we're not actually sure that the quarter degree parameterizations will be able to bring it up enough to help.
Yeah, part of the goal of this was to use these kinds of statistics to validate and maybe improve backscatter parameterizations, but the gap is quite large. So we're hunting that down the road, and we're going to try to do some science with MesaClip first. Any other questions? Got one more talk, and it is Justin. I want to get this thing set up. Yeah, I'll try and get your talk. Yeah. All right. Well, last talk today.
Yeah.
Justin Small. Predictability and precipitation. Go ahead, Justin.
Thank everyone for staying on Friday afternoon for the last talk.
You turn on your mic. Thank you.
Oh, yeah, I think the green light, yeah. And thank you particularly to Ian and Gustavo for organizing the meeting. And as Ian said, ocean eddies and precipitation. And I'm following on from the previous speaker, from Ben, to look at implications for the atmosphere and precipitation, and in particular on predictability and timescales of S2S, so fairly short, few-month timescales. But the reason I'm looking at these timescales rather than longer is a kind of good coincidence and combination of funded by a NOAA grant, which is looking at the grand challenge of predicting precipitation on S2S timescales. And some of the figures they showed, they showed figures saying how poor is prediction of precipitation on those timescales, and they showed the ocean and the land. So I thought, okay, we can look over the ocean as well. So that was the NOAA project. And then the Maserclip project was going on at the same time, producing all these huge amounts of data and nice results that Fred described. And by the way, coincidentally, Fred, I think I've got a very similar front page of my talk. I think that was coincidence. And so I was able to use Maserclip data, and in particular, the high resolution decadal prediction runs, but I'm looking at for S2S. And there's a whole suite of co-authors have contributed a lot, including Ben and Ian Grooms, and I'll show their part later. And this is a busy slide I'll try and skip through. Ben has introduced the importance of ocean mesoscale eddies, and we know that here the focus has been a lot on the net effect on ocean circulation. Can we predict eddies? There have been a few papers looking at prediction of eddies, and they give some timescales of between 3 to 8 weeks in different regions of the globe. But I would say the literature is not very comprehensive. It has different regions and uses a variety of different methods, and not kind of coordinated or anything. Next, can we predict small-scale precipitation? And I'm going to make a broad brush statement that small-scale convection in the atmosphere is hard to predict. I'm hoping there's no atmosphere modeler here to either deny or agree with that, because I don't know much about it. But is there a role for small-scale SST to kind of anchor the convection? And that's what's going to come in this talk. Going to use the HRDP, as I mentioned, focusing on the Northwest Atlantic, because that was one of the NOAA foci. But some findings can be applied globally. I'll maybe show something. I'll use standard community metrics from the predictability community. So I think that's the advantage of the previous literature, which is kind of range of kind of customized metrics. And to investigate mesoscale eddies, I use a simple spatial kind of boxcar filter to isolate scales less than 500 kilometers. It's been used before here, but eddy tracking has also been applied by Ben. The prediction experiment, a little bit more detail here. HRDP, I'm going to skip through. We use the same resolution that Fred has mentioned, fully coupled. Want to emphasize, we're doing perfect model experiments. And the main reason for that is that our eddies are not simulated in the ocean model. That's the main reason. So we're trying to assess, can we predict eddies? They're not assimilated in the ocean model, which is the high resolution FOSI that has been talked about before, I think. Eddies are present, but they're not in the correct location or amplitude. They're a chaotic system. So there's, maybe I'm confusing two issues here at this stage. First of all, I'm not comparing observations. The secondly, it gets a little bit harder because because of data assimilation. I think I've confused myself. Best to just skip on. I'll try and explain as it goes along. Are these perfect models that I compare with? So here are Ben's statistics. Now on the top, let me see. On the left is the satellite data and showing similar things. In the middle is the high-res ocean model, FOSI-HR. And here on the on the top row is amplitude. And you can see there, like Ben was saying for Maserclip, they're kind of in the right ballpark. There are biases in the ocean model, as one expects. Things like the Gulf Stream path, but they are in the same ballpark. Same with the area. These bottom two figures show the area. So it's a good ocean model. It's not exactly perfect. Quite perfect might be the description. And then part two of perfect model is I'm going to be looking at an air-sea interaction piece, basically related to precipitation. So how well does our coupled model do compared to satellite data for the relationship of SST and precipitation? And I'm going to skip through this quickly because I could spend a lot of time identifying differences and kind of complaining, doing things like that. But again, it's in the right ballpark. Observations are on the top left. This is the correlation of monthly precip and SST. And I boxed the kind of boundary current eddying regions, and you see regions of positive correlation. ERA 5, top right, a lot of the ERA 5 performance is due to parameterization rather than data assimilation. So like one of you, like Fred, I think mentioned, you can take it with a pinch of salt. The high-res CSM is that middle left. And interestingly, there's a difference between the fully coupled high-res and next to it is the atmosphere-only high-res, so the quarter-degree atmosphere over an SST product. And they're quite different. And this is the kind of area where I could go on too long. A low-res model's in the bottom. And just in case you think it's weird, the low-res atmosphere only actually gets a strong signal. So this is 1 degree atmosphere, but it's forced by observed SST, which has eddies. And interestingly, with the 1 degree atmosphere, you get quite a strong response to the SST, even though it's only 1 degree. And Ping Chang is co-author. I believe that's due to kind of deficiencies with the convective parameterization in the 1 degree, maybe. So it's kind of too strong a response. So it's mildly perfect, the models that I'm looking at, in summary. Let's now go to looking at the results. So I'm looking at predictability of eddies. As in the first part, I'm going to focus on SST. And these are small scale features. I apply a high pass spatial filter. Top row is from, in this case, perfect model, FOSI open model, and it's for month 1, month 2, month 3. If I can use a cursor. So there's 3 months. You see the eddy signatures in SST. And then the middle row is the ensemble mean from the high resolution decadal predictability experiment, initialized in that first month, moving on through the 3 months. And the colors in the middle row are from HRDP, and the contours are from the FOSI that is trying to predict. And if you look closely, it's quite good matching. So that's encouraging. This is over a 3-month period. And another way to look at it is to consider the spread or the ensemble standard deviation. It's nearly zero month 1, it grows in month 2, and it's more in month 3 again. Now, after 3 months, the skill degrades, and I'll give official skill scores in the next slide. But just as an example, this is 12th month, signal in the middle, the colors are fairly weak, you haven't got much signal, the spread is fairly large, and on the right for comparison is the natural variability, standard deviation. And you can see the spread is going towards the natural variability. So at this point, 12 months, it's not predicting the Gulf Stream eddies very well. So now before I show a number of slides, maps with kind of red colors on it, let me tell you what they're all about. These are predictability metrics. If I was talking to the predictability group, they'd know all this. Some of you might know it, some of you may not. First of all, anomalies are relative to appropriate climatologies. And for the prediction system, it's lead time dependent due to model drift. And you can see from papers by Steve, full descriptions of these. Anomaly correlation coefficient is a bit different to the correlation that Ben was showing. It correlates the anomalies in the HRDP signal and the FOSI perfect model across start dates. And here the signal is defined as the ensemble mean. It's correlation, so that mainly gives phase information. Next one, mean square skill score, kind of enhances the ACC to take into account the amplitude of signals, and whether it's capturing the amplitude well. Finally, well, turns out to be quite a useful metric, signal to total, S2T, ratio of the standard deviations of the signal and the standard deviation of the total variability of HRDP. This is equivalent to saying how well does the model predict itself. It's only using HRDP, it's not comparing with the FOSI. And it's also equivalent to correlation between the signal and individual ensemble members. Like how well, it's like taking the HRDP as individual members of the HRDP as one realization of the real world. So I start to show these skill scores now. This is now showing from left to right, first month, second month, third month. Top panel is anomaly correlation coefficient. The pink and red colors are high values. And you can see for first month, very high, above 0.9, and then it starts to degrade. By the third month, what you see is on the Eastern Basin, it's still quite high, these pink colors, but it's degrading in the Gulf Stream eddying region because the chaotic eddies are not so predictable. But it's still above 0.5 in the ACC, the anomaly correlation coefficient. If you go down to the mean square skill score, because it's also measuring amplitude, in general, the score is lower. It's harder to get it right. And you see the Gulf Stream starting to get less predictable, month 3, but it is still predictable on the eastern side of the basin. And in a minute, I'll show time series averaged over these west and east side of the basin. And just quickly, this is the signal to total metric. It tends to be higher than the other metrics. If I just kind of scoop between the two, because it's just looking at the same model. So you kind of expect it to be a bit higher. So there's the first 3 months there. And you can look globally. This is the ACC for month 3 globally. And as well as the kind of things I've shown already, you've noticed the tropics, the skill goes away very quickly. That hardly lasts a month. Same with high latitudes. I should point out that these are for small scale features. This is specific for small scale features. So different for the large scale, obviously, NSERC and so on. And by month 12, everything has weakened, but you still have these regions of predictability. And I think there may be coincident with the kind of convergence zones in the ocean and kind of plastic garbage patches where there's kind of very slow motion, and maybe easier to predict, less going on. And if you now look at daily data and look at how the skill changes with time, you see the time scale, say this is for SST for the Gulf Stream, say the ACC, which is a solid line, passes 0.6 after about 70 days. So that's the kind of time scale we're thinking of. I also show on these plots persistence, which is the thin line, and that does surprisingly badly. And the thought behind that was, well, maybe the eddies don't move much in the first few months. Maybe you can just predict it with persistence. But that's wrong. And it's really saying the advection and other processes, dynamical processes in the model are needed to get this prediction. It's not just they hang around in the same place for a bit. Now I'm going to relate to the atmosphere. So a top row is some SST cases again, high pass filtered. Bottom row now is convective precipitation from the model. And I've overlaid on the convective precipitation the SST contours from above. And you can see there's a relationship. It may be a little bit strong in the model, but this goes back to the question of whether it's moderately perfect or not. But you see this relationship. This is a case study. You can do correlations across using the high numbers of data. I'm just pointing out this figure is not a skill score. This is just correlating SST and precip like showed in the earlier slide from observations. Now this is from HRDP. If you use 10 members on the left, you get this high correlation. There's a zoom on the top. And you can compare it against one member on the right. It's a weaker correlation. And the one member is like the real world. And actually, Ben Kerbman has written about this. So this is not novel, but you can see it interestingly in HRDP. What is novel is these results are the skill score for precipitation. And I'm using the signal to total skill score because I have to compare within the model itself. And you see in this region, in the first month, high correlation generally, and particularly in the kind of Gulf Stream region. Third month, the Gulf Stream path is highlighted as a maximum. And then by the fifth month, you're starting to weaken and shift towards the coast. And I think that's because you're actually moving away from the high eddy variability. So the thoughts behind this is we have the SST and we know it's fairly predictable up to about 3 months, but after that, it gets less predictable. Then the precipitation responds to the SST. So if you know the SST, you might know something about the precipitation. And that lasts till about 3 months. And then afterwards, you'll get a lowering of skill. That is all for high-pass filtered HRDP. And then this was a suggestion from Ping Chang to compare it to the low res and to compare with unfiltered. So this is all for the third month. On the left is the result just showed in the previous slide from the filtered data, HRDP. In the middle is unfiltered data. And I was actually surprised it's still strong in the unfiltered data. And it's due to this small scale stuff. On the right is the DPLE. And of interest, it does show some predictability. The yellow colors there are on 5.6. And it's in some of the same regions that you see with the HRDP. So it's capturing some of it, but the score is weaker. So I suspect there is some variability of SST in the low res, and there's basically you have the same type of atmosphere model. You get a response to it that is distant. That's probably where I should wrap up. And I'm probably running out of time. You can read the conclusion. Let me talk about limitations and way ahead. Limitations, I've only focused on convective precipitation. That is the part that in the model and in ERA 5 responds to SST. you look at the other part of the precipitation, the large scale result, it doesn't respond. The convective precipitation is about, I think, about 1/2 of the total climatology precip in this region in CSMHR. So you're predicting 1/2 of the precipitation. The other half, you're probably not predicting well. I should check that, but I expect there'll be a low predictability for the large scale precip. Second, well, I'm looking over the ocean. So I'm not, impacts over land are not covered here. And in the way ahead, we hope to look at larger scales. Third limitation is, was it really a perfect model? And that can be discussed. And also in the way ahead, I've already looked at different timescales from daily to monthly, and you can kind of do a timescale distinction. But I'll wrap up there, for the sake of time. Let everyone have Friday afternoon.
Questions? Personal mind. Dan.
I was wondering, and maybe this never, I don't totally understand the distinction between persistence and predictability, but can you have a sense of whether we can characterize some of this very long timescale predictability as kind of the persistence of the autocorrelation of these features?
I was only kind of guessing for the regions that have long predictability. I think actually a better explanation I did not give, but some of the areas where have high predictability up for a number of months are kind of in quiescent regions, but it could be small amplitude SST signal, but I think like Rossby waves or wave-like features, which may be predictable and less chaotic than the Gulf Stream and the boundary currents. So that may be another way to think about it, but I haven't explored it in detail.
It is interesting that your predictability timescale is about 3 months, which is also the average lifetime of a mesoscale eddy in the ocean, 3 months.
Justin, could you remind us how the ensemble spread is generated in the HRD?
Yeah, it's just an atmosphere. Yes.
Okay. So there's no perturbation in the initial ocean state. They're all perfect.
Yes. Yeah, and I think that's, so I think these results will score higher than if you're comparing with observations where you don't have a perfect initial state. My guess is having the perfect initial state in the ocean is helping a lot to have a good score.
All right, well, we're a little bit over. Thank you, Justin. I think we'll stop. Thanks all of the participants, all the speakers, and everyone for being here. And I look forward to doing this again next year.
Thank you for organizing.